Imagine a star so strange, so elusive, that it could completely redefine our understanding of the universe. A star that sits on the razor's edge between the densest stars we know, neutron stars, and the mysterious depths of black holes. Scientists call these hypothetical objects quark stars. If they exist, they're unlike anything else in the cosmos, holding within them the building blocks of the universe itself. But what are quark stars, and why do they matter? Could they hold the answers to some of the most profound questions about space, matter, and the very fabric of reality? Stick around, because this is where science meets the edge of imagination, and the mysteries are deeper than you can possibly imagine. To understand quark stars, we first need to rewind and look at neutron stars, which are already one of the most extreme objects in the universe. When a massive star runs out of fuel, its core collapses under the crushing force of gravity, leaving behind a compact object made almost entirely of neutrons. These stars are so dense that a single teaspoon of neutron star material would weigh about 4 billion tons. Yet, neutron stars aren't the end of the story. If the collapsing star is even more massive, the core could theoretically compress beyond the neutron star stage, into an even denser and more exotic form of matter. This is where quark stars come into play. Quark stars are thought to form when the pressure inside a collapsing star is so intense that neutrons themselves break apart into their constituent particles, quarks. Quarks are fundamental particles, the smallest building blocks of matter, and they combine in groups of 3 to form protons and neutrons. In a quark star, the neutrons are no longer intact. Instead, you have a sea of free-floating quarks. This state of matter is called quark matter, and it's so dense and extreme that it challenges our understanding of physics. Now, here's where things get really interesting. Quark stars could explain some of the unexplained observations we've made in space. For instance, some neutron stars seem to be too small or too massive to fit the models we've created for them. Quark stars, being denser and more compact, could account for these anomalies. But proving their existence isn't easy. They would look almost identical to neutron stars from a distance, and their differences would only show up in their size, mass, or the way they interact with their environment. Theoretical physicists have proposed that quark stars could even glow in unique ways. Because of their extreme density, their surface might emit strange bursts of radiation, unlike anything we've seen from regular stars. This could include flashes of gamma rays or other high-energy phenomena, giving us potential clues to look for. But quark stars don't just raise questions about the stars themselves. They challenge the very foundations of how we understand matter. Quark matter, if it exists, could behave in ways that are completely alien to us. For example, some theories suggest that quark matter might be a perfect fluid, meaning it flows with zero viscosity. This would make it unlike any substance we know on Earth. Some scientists even speculate that inside a quark star, quarks could pair up in a way that creates a superfluid or a superconductor, allowing electricity or heat to move through it with perfect efficiency. The implications of this are mind-boggling. If we could understand how quark matter works, it could unlock new technologies or help us understand the conditions of the early universe, just moments after the Big Bang. After all, the universe itself might have been a sea of free-floating quarks before cooling down and forming the particles and atoms we see today. There's also a tantalizing idea that quark stars might not just be a fleeting stage in a star's life, but could exist as stable objects for billions of years. If that's true, they could be scattered throughout the universe, hiding in plain sight. Astronomers have proposed using advanced telescopes and gravitational wave detectors to look for them. When two quark stars collide, they might create unique gravitational wave signatures that differ from neutron star mergers or black hole collisions. These ripples in spacetime could be the smoking gun we need to confirm their existence. And then there's the possibility of strange matter. Some scientists theorize that in the extreme conditions of a quark star, quarks could rearrange themselves into a new form of matter called strange quark matter. This type of matter, if it exists, could be the most stable form of matter in the universe. It's even been suggested that strange matter could spread like a virus, converting any regular matter it touches into more strange matter. While this sounds like the stuff of science fiction, it's a serious hypothesis that physicists are actively studying. But quark stars also force us to confront some uncomfortable truths about the universe. For one, they highlight just how little we know about the behavior of matter under extreme conditions. Our current theories of physics, including quantum mechanics and general relativity, struggle to fully describe what happens inside a quark star. This is a frontier of science where we have more questions than answers. Quark stars also sit at the intersection of several cosmic mysteries. For instance, they might help us understand dark matter, the mysterious substance that makes up most of the universe's mass. Some researchers have speculated that quark stars could be connected to dark matter in ways we don't yet understand. Perhaps dark matter is made up of exotic particles that are related to quarks, or maybe quark stars could act as factories for these particles under certain conditions. And then there's the question of black holes. If quark stars represent the stage between neutron stars and black holes, could studying them help us understand how black holes form? Could they be the missing link in the life cycle of massive stars? These are the kinds of questions that keep astronomers and physicists up at night. But what's truly humbling about quark stars is the reminder that the universe is far stranger than we can imagine. Every time we think we've figured out how the cosmos works, we discover something new that forces us to rethink everything. Quark stars are a perfect example of this, a theoretical possibility that could upend our understanding of the universe and our place in it. If quark stars exist, they may not only be a cosmic curiosity but a key to answering some of the deepest questions about the universe. These objects could help bridge the gap between theory and observation, offering insights into the fundamental forces that govern everything around us. They remind us that the universe is not static, it is a dynamic, ever-evolving mystery that challenges our understanding at every turn. One of the most fascinating aspects of quark stars is how they might form. Scientists theorize that they are born from the remnants of supermassive stars, which collapse under their own gravity. When a star's core collapses, it compresses into a neutron star. But if the mass is great enough, the pressure could become so intense that it forces neutrons to break apart into their constituent quarks. This process creates an entirely new state of matter, denser and more exotic than anything we can replicate on Earth. Unlike neutron stars, which are primarily composed of neutrons with a thin crust of regular matter on the surface, quark stars would be almost entirely made up of free quarks. This makes them potentially even smaller and denser than neutron stars. To put this into perspective, a typical neutron star has a radius of about 10 kilometers, but a quark star of the same mass could be just a few kilometers across. The density of such an object would be almost unimaginable, many orders of magnitude greater than anything we've observed in nature. One of the challenges in studying quark stars is that they are likely extremely rare, and their properties are so extreme that they are difficult to distinguish from neutron stars. From Earth, both types of stars would look very similar, emitting light and radiation in similar ways. However, subtle differences in their mass, radius, and the way they cool over time might offer clues. For example, quark stars might cool faster than neutron stars due to their unique internal composition. Observing these cooling patterns could be one way to identify them. Another intriguing possibility is that quark stars could rotate at incredible speeds. Neutron stars are already known for their rapid rotation, some spin hundreds of times per second, but quark stars, being even smaller and denser, could spin even faster. These rapid rotations could produce unique electromagnetic signals, such as bursts of gamma rays or X-rays, that astronomers could detect with sensitive instruments. The study of quark stars is not just about understanding exotic states of matter, it's also about pushing the boundaries of our physical theories. For instance, the behavior of quarks inside a quark star could help scientists refine their understanding of quantum chromodynamics, QCD, the theory that describes how quarks interact via the strong nuclear force. QCD is notoriously difficult to test in laboratory settings because the energy levels required to study quarks directly are so extreme. But quark stars could act as natural laboratories, providing indirect evidence for how quarks behave under the most extreme conditions. Furthermore, quark stars might shed light on the mysterious phenomenon of strange quark matter. In normal matter, quarks come in three types: up, down, and strange. While up and down quarks are common in the protons and neutrons that make up regular matter, strange quarks only appear in extreme environments, such as those found inside quark stars. Some scientists believe that strange quark matter could be stable and might even exist independently of quark stars, potentially forming tiny, stable particles known as strangelets. If strangelets exist, they could have profound implications for our understanding of the universe, as they might represent a new form of matter with unique properties. The search for quark stars is part of a broader effort to understand the life cycles of stars and the cosmic forces that shape them. By studying these exotic objects, scientists hope to answer questions about how matter behaves at the smallest scales and under the most extreme conditions. These insights could have practical applications as well, potentially informing the development of new materials or technologies that take advantage of the unique properties of quark matter. But the implications of quark stars go even further. They challenge us to think about the nature of existence itself. What does it mean for something to be stable or unstable? How do the fundamental forces of the universe interact to create the structures we see in the cosmos? And what can these extreme objects teach us about the early moments of the universe, when everything we know today was compressed into a state of unimaginable density and heat? Quark stars also raise philosophical questions about the limits of human knowledge. Even if we were to observe one of these objects directly, would we truly understand it? Or would it remain an enigma, a reminder of how much we have yet to learn about the universe? These are questions that scientists and philosophers alike grapple with, and they are a testament to the enduring mystery and wonder of the cosmos. The search for quark stars is a journey into the unknown. It requires us to push the boundaries of our technology, our theories, and our imagination. It's a reminder that science is not just about answering questions, it's about asking new ones and embracing the uncertainty that comes with exploring the frontiers of knowledge. Quark stars are more than just a scientific curiosity. They are a symbol of the endless possibilities that lie beyond our current understanding. They remind us that the universe is far more complex and wondrous than we can imagine, and that the pursuit of knowledge is a journey without end. Whether or not we ever find definitive proof of quark stars, the search for them will undoubtedly lead to new discoveries, new ideas, and new ways of thinking about the cosmos and our place within it. The search for quark stars also intertwines with the study of black holes, as they represent the boundary between two of the most enigmatic and extreme phenomena in the universe. Black holes, with their intense gravitational pull, are thought to form when massive stars collapse completely, leaving behind a singularity surrounded by an event horizon. Quark stars could serve as a transitional phase, existing in a delicate balance where the pressure from degenerate quark matter resists complete collapse into a black hole. If this is true, then quark stars might hold the key to understanding what happens at the threshold between extreme density and total collapse. Moreover, quark stars could help solve the mystery of ultra-dense neutron stars. Observations of certain neutron stars suggest that they are too heavy to remain stable as traditional neutron stars but not massive enough to become black holes. These so-called overweight neutron stars might, in fact, be quark stars in disguise. By reanalyzing the data from telescopes and observatories, scientists could potentially identify telltale signs of quark matter within these objects, further refining our understanding of stellar evolution. One of the most fascinating implications of quark stars lies in their potential to challenge the Chandrasekhar and Tolman-Oppenheimer-Fokoff limits, which describe the maximum masses for white dwarfs and neutron stars, respectively. If quark stars exist, they would redefine these boundaries, adding a new layer of complexity to our understanding of stellar collapse. This could, in turn, reshape how we model the life cycles of stars, the formation of black holes, and the behavior of matter under extreme conditions. The existence of quark stars also raises profound questions about the role of exotic matter in the universe. If quark matter is stable at the densities found within these stars, it could imply that such matter might exist elsewhere in the cosmos, perhaps in isolated regions or even as remnants of the Big Bang. This opens up the tantalizing possibility that quark matter could play a role in the large-scale structure of the universe, influencing everything from galaxy formation to dark matter distribution. Dark matter, in particular, remains one of the greatest mysteries in astrophysics. While quark matter is not currently considered a leading candidate for dark matter, the study of quark stars could provide indirect insights into the nature of this elusive substance. For instance, understanding how quarks behave under extreme conditions might reveal new properties or interactions that could explain some of the observed effects attributed to dark matter, such as gravitational lensing or the rotation curves of galaxies. On a more speculative note, quark stars might even serve as natural laboratories for exploring the unification of forces in physics. In the incredibly dense environment of a quark star, the strong nuclear force, which binds quarks together, operates at scales far beyond what we can achieve on Earth. By studying these stars, scientists could gain insights into how the strong force behaves at high energies and how it might connect with other fundamental forces, such as electromagnetism and gravity. This could bring us closer to a grand unified theory, a long-sought goal in theoretical physics. Quark stars might also have implications for understanding the early universe. The conditions inside these stars are thought to resemble those that existed just moments after the Big Bang, when the universe was a hot, dense soup of free quarks and gluons. By studying quark stars, scientists could gain a better understanding of this primordial state and the processes that led to the formation of the first protons, neutrons, and atomic nuclei. This, in turn, could help us unravel the mysteries of cosmic inflation, nucleosynthesis, and the formation of large-scale cosmic structures. But how do we find these elusive objects? Current efforts rely on a combination of observational astronomy, computer modeling, and experimental physics. High-energy observatories like the Chandra X-ray Observatory and the upcoming James Webb Space Telescope are well-suited for detecting the unique radiation signatures that quark stars might produce. For instance, the rapid cooling rates of quark stars could produce distinctive X-ray emission patterns, while their dense, compact nature might cause unusual gravitational effects that could be detected through precise measurements of pulsar timing or gravitational wave signals. In addition to direct observation, laboratory experiments on Earth are pushing the boundaries of what we know about quark matter. Facilities like the Large Hadron Collider, LHC, and the Relativistic Heavy Ion Collider, RHIC, are designed to recreate the extreme conditions needed to study quark-gluon plasma, a state of matter thought to exist inside quark stars. By smashing heavy ions together at nearly the speed of light, scientists can generate temperatures and pressures comparable to those found in the cores of these exotic stars. While these experiments only last for fractions of a second, the data they produce offers valuable insights into the behavior of quarks and gluons under extreme conditions. This, in turn, helps refine the models used to predict the properties of quark stars. One intriguing avenue of research involves gravitational waves, ripples in space-time caused by massive cosmic events. The detection of gravitational waves from neutron star mergers by LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo has opened a new window into the study of dense objects. If quark stars exist, their collisions or mergers would likely produce unique gravitational wave signatures. These signals could be distinct enough to differentiate quark stars from neutron stars or black holes, providing a direct way to identify these elusive objects. Furthermore, the electromagnetic afterglows of such collisions, which include bursts of gamma rays, X-rays, and visible light, could also carry the fingerprints of quark matter. These events, known as kilonovae, result from the radioactive decay of heavy elements formed during the merger. If quark stars are involved, the chemical composition and energy output of the kilonova could differ from those of typical neutron star mergers. This makes multi-messenger astronomy, combining gravitational wave and electromagnetic observations, a powerful tool for probing the existence of quark stars. The implications of quark stars extend beyond astrophysics and into the realm of cosmology. For example, the study of these stars could provide clues about the distribution of matter and energy in the universe. If strange quark matter, or strangelets, is stable and abundant, it could contribute to the overall mass of the universe in ways that we have yet to understand. This could help resolve discrepancies in our measurements of the universe's expansion rate, or the so-called Hubble tension. Additionally, quark stars challenge our understanding of what defines a star or a compact object. Traditionally, we categorize celestial objects based on their mass, composition, and behavior. But quark stars blur these lines, existing in a liminal space between neutron stars and black holes. This raises philosophical questions about classification and the limits of human knowledge. How do we define something that defies our current understanding? And what other unknown states of matter or cosmic phenomena might exist beyond the reach of our instruments and theories? The quest to understand quark stars is not just a scientific endeavor, it's a testament to human curiosity and our desire to explore the unknown. These objects remind us that the universe is full of surprises and that each discovery opens the door to new questions and possibilities. They challenge us to think creatively, to push the boundaries of our imagination, and to embrace the uncertainty that comes with exploring the frontiers of knowledge. It's worth noting that the search for quark stars is still in its infancy. While the theoretical groundwork has been laid, direct observational evidence remains elusive. This is partly because the differences between quark stars and neutron stars are subtle and require incredibly precise measurements to detect. It's also because quark stars, if they exist, are likely rare and short-lived, making them difficult to find. Despite these challenges, advances in technology and methodology are bringing us closer to uncovering the truth. The discovery of a quark star would be a groundbreaking moment in astrophysics, comparable to the detection of the first pulsar or the imaging of a black hole's event horizon. It would confirm the existence of a new state of matter and provide a wealth of data for testing our theories of particle physics, quantum mechanics, and general relativity. It would also inspire new generations of scientists and engineers to continue the search for answers to the universe's deepest mysteries. Quark stars are a reminder that the cosmos is far more complex and wondrous than we can imagine. They challenge our understanding of the laws of physics and the nature of reality itself. They invite us to think about the universe not as a static collection of objects but as a dynamic, ever-changing tapestry of forces, particles, and phenomena. And they remind us that, no matter how much we learn, there will always be more to discover. As we continue to explore the universe, we must remain open to the possibility that our understanding will evolve. Quark stars, if they exist, are a testament to the idea that science is not just about finding answers but about asking better questions. They remind us that the pursuit of knowledge is a journey, not a destination, and that the universe is a vast and mysterious place, full of wonders waiting to be uncovered. The potential discovery of quark stars could revolutionize how we perceive the life cycles of stars and the intricate processes governing stellar evolution. For instance, if quark stars are confirmed to exist, they might represent an additional phase in the collapse of massive stars. This would reshape existing models of stellar death, requiring scientists to integrate quark stars as an intermediate stage before the formation of black holes. Such an adjustment could redefine how we understand the distribution of these enigmatic objects across the cosmos. The implications for nuclear physics are equally profound. Quark stars would represent a natural laboratory for studying matter under conditions that cannot be replicated on Earth. The behavior of quarks, particularly the interactions governed by the strong nuclear force, remains one of the least understood aspects of particle physics. Quark stars might offer answers to questions about the stability of quark matter and the conditions required for its existence. For example, could quark matter exist outside of stars? Or is it confined to the extreme pressures found within their cores? If quark matter can exist independently, it might have profound implications for cosmology, including the formation and evolution of galaxies. A particularly captivating concept tied to quark stars is the possibility of strange matter. This hypothetical state of matter is thought to consist of up, down, and strange quarks in equal proportions. Some physicists believe that strange matter might be more stable than ordinary nuclear matter. If this is true, quark stars could be predominantly composed of strange matter, earning them the alternate title of strange stars. The stability of strange matter raises intriguing possibilities, including the idea that it could spread like a contagion. If a strange star came into contact with a neutron star, it might convert the neutron star into another strange star. While this is purely speculative, It underscores the exotic and potentially transformative nature of these objects. Another exciting avenue of research involves understanding the role of quark stars in the context of dark energy. Dark energy is the mysterious force driving the accelerated expansion of the universe, but its origin and properties remain elusive. Some theories suggest that quark stars, or the processes involved in their formation, could generate unique energy signatures or interact with dark energy in unexpected ways. While these ideas are highly theoretical, they highlight the interconnected nature of cosmic phenomena and the potential for quark stars to inform multiple areas of research. Quark stars might also serve as a bridge between the microscopic and the macroscopic, linking the physics of subatomic particles to the behavior of massive celestial objects. This dual role makes them a unique subject of study, as they challenge the traditional boundaries between disciplines like astrophysics, particle physics, and quantum mechanics. By studying quark stars, scientists can explore questions that lie at the intersection of these fields, such as how quantum effects manifest on astronomical scales or how gravity interacts with the strong nuclear force. The search for quark stars also underscores the importance of collaboration in scientific research. Theoretical physicists, observational astronomers, and experimental scientists must work together to develop and test hypotheses about these elusive objects. This collaborative approach is already yielding results, as advances in technology and computational power enable more detailed simulations and more sensitive instruments. For example, next-generation telescopes like the Square Kilometre Array (SK), and space-based observatories like the European Space Agency's Athena mission are poised to detect faint signals that could reveal the presence of quark stars. Beyond their scientific significance, quark stars capture the imagination because they represent a boundary between the known and the unknown. They challenge us to think about what lies beyond our current understanding and to consider the possibility that the universe is stranger than we can comprehend. This sense of wonder is a driving force behind scientific discovery, inspiring researchers to push the limits of what is possible. In a broader sense, the study of quark stars reflects humanity's enduring quest to understand our place in the cosmos. By investigating these exotic objects, we are not just learning about the universe but also about ourselves and our capacity for curiosity, creativity, and exploration. Quark stars remind us that the pursuit of knowledge is a deeply human endeavor. While the journey to uncover the truth about quark stars is far from over, each step brings us closer to answers that could redefine our understanding of the universe. Whether or not these objects exist, the search for them has already expanded the boundaries of science, inspiring new questions and opening new avenues of research. The story of quark stars is a testament to the power of curiosity and the enduring allure of the unknown, a reminder that the universe is vast, mysterious, and full of wonders waiting to be discovered. As we continue to gaze at the stars, we must remain open to the possibility that they hold secrets we have yet to imagine. Quark stars, with their strange and exotic properties, are a symbol of the infinite complexity of the cosmos and a reminder that our journey of discovery has only just begun. The journey into understanding quark stars leads us to reimagine the very nature of the universe. These objects challenge some of the most deeply held assumptions in astrophysics and particle physics. For instance, one of the foundational ideas in astrophysics is the concept of degeneracy pressure, which is the force that prevents certain stars from collapsing under their own gravity. In white dwarfs, electron degeneracy pressure halts the collapse, while in neutron stars, neutron degeneracy pressure plays this role. However, in quark stars, these traditional forces might give way to something far more exotic. In quark stars, it is believed that the degeneracy pressure is provided not by electrons or neutrons, but by quarks themselves. This implies that the conditions inside these stars are so extreme that matter no longer exists in its familiar forms. Instead, protons and neutrons are broken apart into their constituent quarks, forming a quark-gluon plasma. This plasma is a state of matter where quarks and gluons, which are normally confined within particles, move freely. It's a bizarre and alien environment, one that resembles the conditions thought to exist in the universe just moments after the Big Bang. This connection to the early universe is one of the most fascinating aspects of quark stars. By studying them, scientists can effectively peer back in time to the earliest moments of cosmic history. The extreme conditions inside quark stars mirror those that existed in the first few microseconds after the Big Bang, making these stars natural laboratories for studying the origins of the universe. This could provide answers to some of the most profound questions in cosmology, such as why the universe contains more matter than antimatter or how the first elements were formed. Quark stars also have implications for our understanding of gravity. In Einstein's theory of general relativity, gravity is described as the curvature of spacetime caused by mass and energy. While this theory has been incredibly successful at explaining a wide range of phenomena, it breaks down under the extreme conditions found in black holes and, potentially, quark stars. Studying quark stars could provide new insights into the behavior of gravity under such conditions, offering clues about how to reconcile general relativity with quantum mechanics, a major goal of modern physics. Moreover, quark stars might play a role in some of the universe's most violent events. When massive stars collapse, they can give rise to supernovae, gamma-ray bursts, or even black holes. If quark stars exist, they could represent an intermediate stage in this collapse. For example, a collapsing star might briefly form a quark star before either stabilizing or continuing to collapse into a black hole. This would make quark stars transient phenomena, appearing only briefly in the aftermath of certain stellar deaths. Detecting these fleeting objects would require incredibly precise instruments, but their discovery could provide new insights into the life cycles of stars and the mechanisms driving some of the universe's most energetic events. Another fascinating possibility is the role quark stars could play in the production of heavy elements. It's well known that elements heavier than iron are formed in extreme environments, such as supernovae or neutron star mergers. If quark stars are involved in these processes, they might contribute to the formation of elements in ways we don't yet understand. For example, the unique conditions inside a quark star could lead to the creation of exotic isotopes or even entirely new elements, adding a new dimension to our understanding of nucleosynthesis. Quark stars also raise questions about the ultimate fate of matter in the universe. If quark matter is stable, it could persist indefinitely, even as the universe continues to expand and cool. This raises the intriguing possibility that quark stars, or remnants of them, could survive long after other forms of matter have decayed. They might represent a kind of end state for matter, providing a glimpse into the far future of the cosmos. The potential stability of strange quark matter also has implications for the search for extraterrestrial life. Some scientists have speculated that strange matter could be used as a source of energy by advanced civilizations. If strange matter is as stable and energy-dense as some theories suggest, it could be an ideal fuel for interstellar travel or other advanced technologies. While this idea is purely speculative, it underscores the far-reaching implications of studying quark stars and their properties. The search for quark stars is also a reminder of the importance of humility in science. Despite centuries of progress, there is still so much we don't know about the universe. Quark stars, if they exist, are a testament to the idea that the cosmos is full of surprises, many of which defy our current understanding. They challenge us to think creatively, to question our assumptions, and to embrace the uncertainty that comes with exploring the unknown. As we continue to study the universe, we must remain open to the possibility that quark stars are just one piece of a much larger puzzle. The discovery of these objects would not only answer some questions but also raise many more, driving further exploration and discovery. This is the nature of science, a never-ending journey of curiosity and inquiry, fueled by the desire to understand the world around us. The study of quark stars is about more than just science. It's about pushing the boundaries of human knowledge and imagination. It's about asking big questions and seeking bold answers. And it's about recognizing that, no matter how much we learn, there will always be more to discover. The universe is vast, mysterious, and full of wonders, and quark stars are a powerful reminder of just how much there is left to explore. The existence of quark stars might also hold the key to understanding the cosmic balance of forces in the universe. These enigmatic objects could provide critical evidence for the interplay between gravity, the strong nuclear force, and quantum mechanics under conditions that cannot be replicated elsewhere. For example, the strong nuclear force, which binds quarks together within protons and neutrons, operates at subatomic scales and is incredibly powerful. When quark stars form, the strong force might reach unprecedented dominance, creating a state of matter where quarks exist as free particles in a densely packed core. This equilibrium challenges our understanding of phase transitions in matter. In simpler terms, a phase transition occurs when a substance changes its state, like ice melting into water. In the case of quark stars, the transition is from hadronic matter, made of protons and neutrons, to quark matter, a state of free quarks. This is no ordinary phase change. It's a transformation that occurs under pressures and temperatures so extreme that they stretch our current theories to their limits. Scientists speculate that the phase transition to quark matter could be smooth or involve sudden, dramatic changes, like a quark flash, where the entire core converts almost instantaneously. Such phenomena could produce observable signals, like gravitational waves or unique electromagnetic bursts. Gravitational wave observatories like LIGO and Virgo have already detected waves from neutron star collisions, and these detections could hold clues to the presence of quark stars. If a neutron star is on the brink of converting to a quark star, the resulting collision might produce distinctive wave patterns, offering a tantalizing new way to detect these objects. This would be a groundbreaking step forward, as gravitational waves are not only a tool for confirming the existence of quark stars but also a window into the fundamental workings of the universe. The properties of quark matter also raise questions about its potential as a source of energy. If strange quark matter is as stable as some theorists propose, it could release enormous amounts of energy when formed. This energy release might explain some of the most energetic phenomena observed in the universe, such as gamma-ray bursts. Gamma-ray bursts are short-lived but incredibly powerful explosions of electromagnetic radiation, often associated with the collapse of massive stars or the merging of neutron stars. If quark stars are involved, they might provide a new explanation for the origins of these bursts, linking them to the phase transition to quark matter. Another intriguing possibility involves the concept of hybrid stars, which are thought to exist between neutron stars and pure quark stars. Hybrid stars might contain a core of quark matter surrounded by an outer shell of neutron-rich material. These objects could represent a transitional state in the evolution of compact stars, offering insights into how matter behaves as it approaches the limits of density and pressure. Studying hybrid stars might reveal how the properties of quark matter evolve over time, and how they interact with the surrounding neutron matter. Quark stars might also influence the large-scale structure of the universe. For example, their unique properties could affect the distribution of mass and energy in galaxies. If quark stars are more massive or denser than neutron stars, they could alter the dynamics of galactic evolution, influencing the formation of stars, planets, and even black holes. This could have cascading effects on the cosmic web, the vast network of filaments and voids that forms the large-scale structure of the universe. From a philosophical perspective, the search for quark stars challenges us to reconsider what we know about the nature of existence. These objects exist at the intersection of the macroscopic and the microscopic, bridging the gap between the vastness of the cosmos and the subatomic world. They remind us that the universe operates on scales that are both unimaginably large and incomprehensibly small, and that our understanding of reality is shaped by our ability to navigate these extremes. The study of quark stars also serves as a reminder of the power of human ingenuity. The fact that we can even conceive of such objects, let alone devise methods to search for them, speaks to the remarkable capabilities of the human mind. It is a testament to our ability to ask questions, to imagine the unimaginable, and to pursue knowledge for its own sake. This spirit of inquiry is what drives science forward, propelling us toward new discoveries and deeper understandings. As we continue to explore the universe, the mystery of quark stars serves as a beacon, guiding us toward the unknown. Each step in the search brings us closer to answering some of the most profound questions about the nature of matter, energy, and the cosmos itself. Whether or not quark stars exist, the journey to find them has already expanded our horizons, challenging us to think beyond the limits of our current knowledge. The story of quark stars is not just about science, it's about our place in the universe. It's about the curiosity that drives us to explore, the creativity that allows us to imagine, and the determination that compels us to seek answers. Quark stars are a symbol of the mysteries that await us, a reminder that the universe is vast, complex, and full of surprises. As we continue this journey, we must remain open to the possibility that the answers we find will raise new questions, sparking new avenues of exploration. This is the essence of science, a never-ending quest to understand the world around us, driven by a relentless curiosity and a deep-seated desire to know. The exploration of quark stars not only reshapes our understanding of physics but also fuels our curiosity about what might lie beyond them. Could there be objects even stranger than quark stars? Theoretical physics entertains the possibility of even more exotic states of matter, such as preon stars, which are hypothesized to consist of particles smaller than quarks, known as preons. Though purely speculative at this stage, the idea of preon stars extends the logic of quark stars to its next possible extreme. If quark stars challenge our understanding of matter, energy, and gravity, preon stars would upend it entirely. But the beauty of the quark star mystery lies not just in what we don't know, it's also in what we might soon discover. Advances in technology are bringing us closer to the answers. Next-generation telescopes, such as the James Webb Space Telescope, JWST, and the upcoming Einstein Telescope for gravitational wave detection, are already expanding our observational capabilities. These tools are designed to peer deeper into the universe than ever before, capturing faint signals and rare cosmic events that could finally confirm the existence of quark stars. The signals we're searching for aren't limited to light or gravitational waves. Neutrinos, tiny, nearly massless particles that interact weakly with matter, could also hold the key. Neutrinos are produced in vast quantities during supernova explosions, and their behavior might change in the presence of quark matter. A detailed analysis of neutrino emissions from supernovae or neutron star collisions might reveal telltale signs of quark stars. This approach could complement other detection methods, providing a multifaceted view of these elusive objects. Another exciting avenue for discovery lies in the field of numerical simulations. By using supercomputers to model the behavior of matter under extreme conditions, scientists can predict the observable properties of quark stars, such as their mass, radius, and temperature. These simulations help refine our expectations, guiding observational efforts and increasing the chances of a successful detection. They also allow researchers to test competing theories, narrowing down the range of possibilities and focusing on the most promising explanations. The confirmation of quark stars would have profound implications beyond astrophysics. It could impact our understanding of quantum chromodynamics, QCD, the branch of physics that describes the interactions between quarks and gluons. QCD is one of the most complex and challenging areas of modern physics, and real-world data from quark stars could provide critical insights into its workings. This, in turn, could influence other areas of science, from particle physics to cosmology, creating a ripple effect of new discoveries and innovations. Quark stars also push the boundaries of what we consider possible in the universe. They remind us that nature often operates on a level far beyond human intuition. The very idea that matter can be compressed into a state where quarks move freely is difficult to grasp, yet the evidence suggests it might be true. This challenges us to think more deeply about the fundamental nature of reality, encouraging us to question assumptions and embrace uncertainty. The potential existence of quark stars also raises philosophical questions about the universe's complexity and our ability to understand it. Are there limits to human knowledge, or can we eventually unravel even the most intricate mysteries? Quark stars, with their blend of theoretical elegance and observational elusiveness, represent the kind of problem that tests the limits of human ingenuity. They compel us to push forward, even when the answers seem out of reach, because the pursuit of knowledge is valuable in its own right. In a way, the search for quark stars mirrors humanity's broader quest to understand the cosmos. It's a journey filled with uncertainty, but also with moments of profound revelation. Along the way, we learn not just about the universe, but about ourselves, about our capacity for curiosity, creativity, and resilience. Quark stars remind us that the unknown is not something to fear, but something to embrace, for it is in the unknown that we find the greatest opportunities for discovery. As we stand on the brink of a new era in astronomy, the mystery of quark stars serves as a symbol of what lies ahead. With each new observation, simulation, and theoretical breakthrough, we move closer to solving this cosmic puzzle. And as we do, we uncover not just the secrets of quark stars, but the deeper truths of the universe itself. In the vast expanse of space, where stars collapse and black holes form, where matter transforms and energy reigns supreme, the story of quark stars unfolds. It is a story of extremes, of the most powerful forces and the most fundamental particles. It is a story that challenges our understanding and expands our horizons. And it is a story that, in its complexity and beauty, reflects the boundless wonder of the cosmos. Quark stars represent a profound enigma in the tapestry of cosmic phenomena, and their study continues to inspire awe and fascination. Their existence, even as a hypothesis, challenges us to rethink the boundaries of physics and the underlying principles governing the universe. What makes quark stars particularly intriguing is how they straddle the line between the familiar and the uncharted, combining known elements of neutron stars and black holes with entirely new theoretical possibilities. One of the key areas of exploration in understanding quark stars is their role in the life cycle of massive stars. When a massive star exhausts its nuclear fuel, it undergoes a cataclysmic collapse, often resulting in a neutron star or a black hole. However, under certain conditions, if the core's density exceeds a critical threshold, the neutrons themselves may break down into their constituent quarks, forming quark matter. This transformation could stabilize the star, preventing it from collapsing further into a black hole. The result is a quark star, a celestial body suspended in a precarious balance between the inward pull of gravity and the outward pressure of quark degeneracy. This transition is not merely a theoretical concept, it is supported by tantalizing hints from observations. For instance, astronomers have identified neutron stars with masses that approach the theoretical maximum for such objects, around 2.5 solar masses. These so-called massive neutron stars might actually be quark stars in disguise, their true nature hidden beneath a thin crust of neutron-rich material. By studying these objects in greater detail, scientists hope to uncover evidence of the quark matter phase and determine whether quark stars truly exist. The physical properties of quark stars are another area of active investigation. Unlike neutron stars, which are composed primarily of neutrons, quark stars might contain strange quark matter, a form of matter that includes up, down, and strange quarks. Strange quark matter is theorized to be more stable than ordinary matter, which could explain why quark stars might persist for billions of years without collapsing. This stability could also have implications for the detection of quark stars, as it suggests they might emit unique signals that distinguish them from other compact objects. One such signal could be the emission of gamma rays or X-rays. Quark stars, with their extreme densities and high temperatures, are likely to be powerful sources of electromagnetic radiation. Some scientists have even speculated that quark stars could explain certain mysterious phenomena, such as ultraluminous X-ray sources, ULXs, and soft gamma repeaters, SGRs. These objects exhibit unusual brightness and variability, characteristics that might be consistent with the presence of quark matter. Another intriguing possibility is that quark stars could act as natural laboratories for studying the behavior of matter under extreme conditions. In particular, they could provide insights into the equation of state, EOS, of quark matter, a mathematical relationship that describes how matter behaves under varying levels of pressure and density. The EOS of quark matter remains one of the biggest uncertainties in modern physics, and quark stars could hold the answers. Observing and studying quark stars is no easy task, as their distinguishing features are subtle and often masked by their similarity to neutron stars. However, advances in technology and observational techniques are making it increasingly possible to detect these features. For example, the detection of pulsars, rapidly rotating neutron stars that emit beams of electromagnetic radiation, has provided valuable data on the properties of compact objects. If quark stars exist, they might exhibit similar pulsar-like behavior, but with unique signatures that set them apart. The search for quark stars is also being aided by the study of gravitational waves. These ripples in spacetime, first detected in 2015, are generated by the violent collisions of massive objects, such as neutron stars and black holes. If one of the colliding objects is a quark star, the resulting gravitational wave signal could reveal its presence. In fact, some scientists believe that certain features of the gravitational wave signals detected so far might already hint at the existence of quark stars. Beyond their physical properties, quark stars also raise intriguing questions about the nature of the universe itself. For instance, if strange quark matter is stable, it might have been produced in the early moments of the Big Bang, and could still exist in the form of tiny, primordial quark nuggets scattered throughout the cosmos. These nuggets, sometimes referred to as strangelets, could serve as a form of dark matter, the mysterious substance that makes up most of the universe's mass. The connection between quark stars and dark matter is particularly compelling, as it opens up new avenues for exploring the fundamental composition of the universe. If strange quark matter is indeed a component of dark matter, it would provide a direct link between the physics of quark stars and the large-scale structure of the cosmos. This, in turn, could help resolve some of the most enduring mysteries in astrophysics, such as the nature of dark matter and its role in shaping galaxies and clusters. The implications of quark stars extend even further, touching on questions of cosmology, particle physics, and the ultimate fate of the universe. For example, the study of quark stars could shed light on the conditions necessary for the formation of black holes and the potential existence of objects beyond the black hole threshold, such as Planck stars or even exotic states of matter predicted by string theory. In this sense, quark stars are not just an isolated phenomenon but a window into the broader mysteries of the universe. They challenge us to think beyond the familiar, to explore the extremes of nature, and to confront the limits of our understanding. They remind us that the universe is a vast and complex place, filled with wonders that defy easy explanation. As we continue to probe the depths of space, the mystery of quark stars serves as a reminder of the boundless potential for discovery. Each new observation, each new theory, brings us closer to unraveling the secrets of these enigmatic objects. And in doing so, we not only expand our knowledge of the cosmos but also deepen our appreciation for the beauty and complexity of the universe. As our observational technology continues to advance, the possibility of confirming the existence of quark stars becomes ever more tantalizing. The era of discovery that lies ahead promises to reveal the true nature of these cosmic enigmas. The great promise of modern physics, combined with the wealth of data we're gathering from space, brings us closer to understanding the fundamental forces that govern the universe, forces so powerful they can reshape matter itself. The role of quark stars extends far beyond simply offering us a peek into an exotic form of matter. They act as a cosmic laboratory where the fundamental laws of physics, quantum mechanics, general relativity, and nuclear physics collide in extreme environments. Understanding how quark matter behaves at the densities and temperatures found within these stars could transform our understanding of particle interactions, the structure of matter, and the behavior of the universe at its most fundamental level. This knowledge could have far-reaching implications, not just for theoretical physics, but for technology and practical applications down the line. One area where these stars may provide valuable insights is in the realm of high-energy physics. Quark stars, as theorized, would generate vast amounts of energy in the form of radiation. Their study could help us understand the conditions under which fundamental particles such as quarks and gluons can be isolated or manipulated, advancing the development of future particle accelerators and energy experiments. Moreover, they could help illuminate the properties of exotic materials, allowing for the development of materials with unique properties that might be applied in fields like quantum computing, superconductivity, and even energy storage. While the direct observation of quark stars remains elusive, the advances in gravitational wave astronomy provide an exciting new frontier in this search. Gravitational waves are created when massive objects like neutron stars or black holes merge, and they can carry with them a wealth of information about the internal structure of these objects. For quark stars, the way in which gravitational waves propagate through their dense cores could offer distinguishing signatures. These signals would be a key diagnostic tool in confirming the presence of quark stars, potentially providing the first definitive evidence of their existence. The upcoming generation of gravitational wave detectors, such as the Einstein telescope or the Cosmic Explorer, will offer the sensitivity needed to detect these elusive waves and analyze them with unprecedented precision. As we improve our understanding of the gravitational wave signals produced by merging stellar remnants, we may detect subtle variations that could indicate the presence of quark stars. A perfect collision between two quark stars, for example, might generate a gravitational wave signal with distinct features, revealing the strange matter within and potentially identifying it as a quark star. We also have to consider the way quark stars may impact our understanding of astrophysical processes on a larger scale. For instance, they might have a role in the formation and evolution of galaxies. The collapse of massive stars into quark stars could release energy that influences their surrounding environments, helping to seed the formation of new stars, or even driving the dynamics of galaxies themselves. This role could make quark stars a key player in understanding the processes of star formation, galactic evolution, and the distribution of matter throughout the universe. On the other hand, the discovery of quark stars could also provide a crucial clue in unraveling the long-standing puzzle of dark matter. If quark stars are made of strange quark matter, they might offer a solution to the dark matter problem by acting as strangelets, tiny, dense objects that could contribute to the missing mass in the universe. These strangelets could be scattered throughout galaxies, invisible to ordinary telescopes, but detectable via their gravitational influence or through interactions with ordinary matter. Such a discovery would rewrite much of what we know about the universe's composition, pointing to a hidden, exotic layer of matter that forms the scaffolding of cosmic structure. In the end, the search for quark stars isn't just about identifying a new class of astronomical objects. It's about deepening our understanding of the cosmos itself. It's about challenging our assumptions, confronting the unknown, and asking bigger questions about the nature of reality. What is the true structure of matter at its most fundamental level? How do the forces of gravity, electromagnetism, and the strong and weak nuclear forces combine to create the universe we observe? Quark stars may hold the answers to these questions, or they may simply lead us to new, even more profound mysteries. No matter the outcome, the pursuit of quark stars embodies the spirit of scientific inquiry. It's a quest not only for knowledge but for meaning, as we seek to place ourselves within the vast, mysterious cosmos. Whether or not quark stars exist as we imagine them, their investigation will continue to push the boundaries of physics, astronomy, and our understanding of the universe. The journey itself will teach us more about the laws of nature, the forces shaping the cosmos, and our place within it. Quark stars, in their very nature, remind us that the universe is filled with things that are far more complex, more mysterious, and more extraordinary than we could have ever imagined. Their existence challenges the limits of our imagination and promises to reshape the way we see the world around us. We are on the cusp of a new era in the search for understanding, and as our tools improve and our theories evolve, the discovery of quark stars, or their confirmation, at the very least, will be a milestone in human knowledge, marking yet another leap forward in the exploration of the unknown. The implications of such a discovery are vast, but the excitement lies in the journey itself. As we continue to probe the depths of space and the most extreme corners of the cosmos, quark stars will continue to serve as a powerful reminder that the universe is far more intricate and fascinating than we could ever hope to fully comprehend. And yet, despite all the questions they raise and the challenges they present, quark stars hold the promise of discovery. As our understanding of the universe grows, so too does our ability to ask deeper and more meaningful questions about the very nature of existence. The existence of quark stars, if confirmed, will be a testament to our ongoing quest for knowledge, an exciting chapter in the never-ending story of cosmic exploration. The deeper we probe into the mysteries of the universe, the more we uncover the true complexity of the cosmos. The search for quark stars is not just about finding new celestial objects, it's about understanding the very fabric of reality itself. Every new discovery in this field brings us closer to understanding the origins of matter and the fundamental forces that shape the universe. Quark stars represent a key puzzle piece in this grand cosmic mystery. Their potential existence challenges everything we know about the life cycle of stars and the way matter behaves under extreme conditions. If quark stars are real, they may be more common than we think, existing in places and environments we never imagined possible. And as technology advances, our ability to detect and study these objects will only grow. One aspect of quark stars that remains a tantalizing mystery is the way they might form. Current models suggest that quark stars could arise from the collapse of neutron stars under extreme pressures. When a neutron star reaches a certain threshold, its core collapsing inward under the crushing force of gravity, the neutrons that make up the star's dense core could break apart, releasing their constituent quarks. This would lead to the formation of a quark star, a bizarre and extreme form of matter that exists in a delicate balance between the forces holding it together. The process of quark star formation would have profound implications for our understanding of stellar evolution. For one, it might suggest that the ultimate fate of massive stars is far more complicated than we previously thought. Instead of simply collapsing into black holes, some stars could undergo a phase transition into quark matter, creating a new type of star altogether. This theory forces us to rethink our understanding of the stellar life cycle, and may even reshape our understanding of how stars interact with one another in the complex dance of cosmic evolution. If quark stars are indeed the product of neutron star collapse, their existence also raises important questions about the behavior of quarks under extreme conditions. At the heart of these stars, the quarks would be packed so tightly that they would no longer exist as individual particles but instead form a dense, fluid-like state of matter known as quark-gluon plasma. This state of matter, which is believed to have existed shortly after the Big Bang, could hold the key to unlocking some of the deepest mysteries of the universe, including the fundamental nature of gravity and the forces that govern particle interactions. To fully understand quark stars and their implications, we must also look at the role they play in the larger cosmic context. The study of these stars can provide valuable insight into the behavior of matter at the most extreme densities and temperatures. It could help us understand the behavior of matter in the early universe, when conditions were vastly different from what we observe today. By studying quark stars, we may be able to reconstruct the events that took place in the first moments of the universe's existence, shedding light on the fundamental forces that shaped its evolution. The study of quark stars could also provide us with clues about the elusive dark matter that permeates the universe. As mentioned earlier, quark stars might be composed of strange quark matter, which has the potential to contribute to the missing mass in the universe. Dark matter is one of the most mysterious and challenging puzzles in modern physics. We know it exists because of its gravitational effects on visible matter, but we have yet to detect it directly. If quark stars are made of strange quark matter, they could represent a significant piece of the dark matter puzzle. They might be scattered throughout the universe, unseen by traditional telescopes but detectable through their gravitational influence or interactions with other forms of matter. The potential link between quark stars and dark matter underscores the importance of continuing to search for these exotic objects. By studying them, we can not only gain insight into the fundamental nature of matter but also take a step closer to solving one of the most profound mysteries of the cosmos. The discovery of quark stars could lead to a paradigm shift in our understanding of the universe, challenging our current models and pushing the boundaries of theoretical physics. In the coming years, the development of more advanced observational techniques will be crucial in the search for quark stars. Current instruments, such as the Laser Interferometer Gravitational Wave Observatory, LIGO, and the Virgo detector, have already revolutionized our understanding of black hole mergers and other cosmic phenomena. As these instruments improve and more sensitive detectors come online, we may finally be able to detect the unique gravitational waves generated by quark star mergers or other interactions. The ability to capture these signals and analyze them in detail will be a game changer in the search for these mysterious objects. One exciting possibility is that the study of quark stars will also help us better understand the behavior of matter in extreme conditions, such as those found in the cores of supernovae or in the early universe. The intense pressure and temperature within quark stars could provide a natural laboratory for studying the behavior of matter under conditions that are impossible to replicate on Earth. This knowledge could have far-reaching implications for fields like nuclear physics, materials science, and even quantum computing. Understanding the behavior of quark matter could lead to the development of new materials with extraordinary properties, potentially revolutionizing industries and technologies that we rely on today. The role of quark stars in the universe is still largely unknown. Their existence remains theoretical, but the quest to understand them represents one of the most exciting frontiers in modern astronomy and physics. With each new discovery, we move closer to unraveling the mysteries of the cosmos, deepening our understanding of the fundamental forces that shape the universe. The search for quark stars is a journey into the unknown, and while we may not have all the answers yet, the pursuit itself holds the promise of expanding our knowledge and reshaping our view of the universe. As we continue to develop more powerful tools and refine our theories, the discovery of quark stars, if it happens, could be one of the most significant breakthroughs in the history of science. It would open a new chapter in our understanding of the universe, offering us new insights into the nature of matter, the forces that govern the cosmos, and the ultimate fate of stars. The mysteries of the universe are vast, and quark stars may hold the key to unlocking some of the deepest secrets of the cosmos, pushing the boundaries of human knowledge and leaving us with a deeper appreciation for the strange and beautiful universe we call home. The pursuit of understanding quark stars is as much a journey into the unknown as it is an exploration of what lies at the very heart of matter itself. Quark stars could offer a glimpse into the most extreme and fundamental processes of the universe, touching on themes that go beyond traditional astronomy and physics. As we continue to uncover new details about these exotic objects, the implications for our broader understanding of space-time, quantum mechanics, and even the very origin of the universe itself will likely unfold in fascinating ways. One critical aspect of quark stars is their relationship to the fundamental forces of nature, particularly the strong nuclear force. In our everyday world, the strong force holds atomic nuclei together, binding protons and neutrons within an atom. But under the extreme conditions found in quark stars, this force behaves in ways that are not yet fully understood. In these environments, quarks themselves are believed to be able to flow freely, unbound by the usual structures that govern the behavior of matter. The strong nuclear force, which is so powerful in the heart of atoms, becomes the dominant force in quark stars, potentially leading to new insights into the behavior of the fundamental building blocks of the universe. In this context, quark stars could serve as natural laboratories for studying quantum chromodynamics, QCD, the theory that describes how quarks and gluons interact. QCD is one of the key areas of modern physics, and understanding it better could lead to breakthroughs in both fundamental physics and applied science. The extreme conditions inside quark stars could provide a unique testing ground for QCD, offering insight into how quarks behave in high-energy environments and revealing new aspects of the strong force that cannot be studied in conventional laboratories. It's worth noting that quark stars may not just exist in isolation, but may also interact with other celestial objects in ways that could give us more information about their structure and behavior. These stars could be involved in interactions with neutron stars, black holes, and other exotic forms of matter, such as dark matter and strange matter. For example, it's possible that quark stars could be involved in mergers that generate gravitational waves, ripples in spacetime that can be detected on Earth by advanced observatories like LIGO. The signals from these mergers would carry information about the mass, spin, and structure of quark stars, offering an entirely new way to study these elusive objects. If quark stars do exist, they could also have a profound impact on our understanding of the fate of massive stars. When a star runs out of fuel, it undergoes a process of gravitational collapse, which results in either a neutron star or a black hole. But what if some stars went one step further, collapsing into quark stars instead? This question raises fundamental issues about the ultimate death of stars and the various stages of stellar evolution that could lead to the formation of exotic objects like quark stars. Understanding this process could give us crucial insights into the life cycle of stars and the ways in which they influence the surrounding space. A critical question that arises in the context of quark stars is whether they might be more common than we currently suspect. While neutron stars and black holes are relatively well understood and have been observed in large numbers, quark stars remain theoretical. Could quark stars be lurking in the universe, undetected by our current instruments? The answer to this question depends on the properties of quark stars themselves. If these stars are stable and long-lived, they could be present in many regions of the universe, potentially in places where the conditions are just right for their formation. The detection of such stars would require us to develop more advanced observational methods capable of detecting their unique signatures, something that is still a significant challenge for modern astronomy. As we attempt to locate these elusive stars, we must also consider the broader implications of their existence. The discovery of quark stars would not only challenge our understanding of stellar evolution but could also provide us with insights into other areas of physics, including the nature of dark energy, the role of gravity in extreme environments, and the possibility of new states of matter. The universe is full of strange and exotic objects, and quark stars could represent one of the most fascinating discoveries in recent decades. Moreover, quark stars could hold the key to unlocking some of the most profound mysteries of the universe itself. For instance, they could provide insight into the conditions that existed during the earliest moments after the Big Bang. Just as quark-gluon plasma was present in the infant universe, quark stars might represent a unique link to that primordial phase. By studying the properties of quark stars, we may be able to peer further back in time, closer to the moment when the universe first began to form and evolve. Understanding how quark matter behaves in these extreme environments could bring us closer to answering some of the most fundamental questions about the origins of the universe. The study of quark stars also invites us to think about the boundaries between different forms of matter. In some ways, they represent a transition between the known forms of matter that make up our everyday world and the exotic, unknown forms of matter that could exist at the extremes of spacetime. Quark stars bridge the gap between neutron stars, which are made up of densely packed neutrons, and black holes, which represent the ultimate collapse of matter. If quark stars truly exist, they could help us understand the boundary between the ordinary and the extraordinary, shedding light on the deep connections between different types of matter and the forces that govern them. One exciting prospect for the future is the potential to simulate quark stars in laboratory settings. While we can't yet replicate the extreme conditions inside a quark star, advances in high-energy particle physics might bring us closer to understanding how quarks behave under such intense pressures. By studying quarks in particle accelerators and other experimental setups, we may be able to mimic some of the conditions that exist inside quark stars, enabling us to test our theories and gain new insights into the behavior of matter at the smallest scales. This could have significant implications for fields ranging from nuclear physics to materials science, opening up new possibilities for understanding the fundamental nature of matter itself. As our knowledge of quark stars continues to evolve, we must also acknowledge the vastness of the universe and the many mysteries that remain hidden within it. The more we learn about quark stars, the more we realize how much we still don't know about the cosmos. The search for these stars is just one piece of the puzzle, and it serves as a reminder of the countless other questions that remain unanswered. Quark stars may be the key to unlocking a deeper understanding of the universe, but the journey of discovery is far from over. Ultimately, the search for quark stars is a journey that will shape the future of astrophysics, cosmology, and fundamental physics. These mysterious objects may hold the answers to some of the most pressing questions in science, challenging our current models and expanding our understanding of the universe. As we continue to explore the cosmos, we may one day find ourselves standing on the edge of a new era of discovery, one where the mysteries of quark stars and their role in the universe are finally revealed, transforming our understanding of the cosmos in ways we can only begin to imagine. As we continue our exploration of quark stars and their potential role in the universe, it's important to consider the broader context of stellar evolution and the processes that could lead to the formation of such exotic objects. Quark stars occupy a unique position in the life cycle of stars, existing in a theoretical space between neutron stars and black holes. But how exactly do stars transition from one form to another, And how might quark stars fit into this continuum? In the standard model of stellar evolution, a star's fate is largely determined by its mass. For stars with relatively low to moderate masses, the end result is typically a white dwarf, an incredibly dense remnant that no longer undergoes fusion reactions. For more massive stars, the situation is more complex. As these stars run out of fuel, they undergo a process called supernova explosion, which is one of the most energetic events in the universe. The remnants of this explosion can collapse into a neutron star, which is even more dense than a white dwarf. Neutron stars are incredibly interesting because they are essentially the remnants of massive stars that have undergone a supernova, leaving behind an extremely compact object made almost entirely of neutrons. These stars are so dense that a single teaspoon of neutron star material would weigh several billion tons. However, neutron stars are not the final stop for all stars. For the most massive of stars, the collapse continues beyond the neutron star stage, eventually resulting in the formation of a black hole, a region in space where gravity is so intense that not even light can escape. But between neutron stars and black holes, there may be another possibility: quark stars. The theory behind quark stars posits that in certain conditions, the matter in a collapsing star may not be able to sustain the neutron star state. Instead, the neutrons could break down into their constituent quarks, leading to the formation of a quark star. This process occurs under incredibly high pressures and temperatures, which is why such objects are likely to form in only the most extreme environments. The formation of a quark star depends on a delicate balance between several competing forces. On one hand, the gravitational pressure from the collapsing star tries to push all of the matter inward, creating a dense core. On the other hand, the strong nuclear force within the neutrons and protons tries to resist this collapse. In a neutron star, this balance is reached when the neutrons themselves are packed closely together, and the force of gravity is counteracted by the strong force between the particles. However, when the star is massive enough, the pressure becomes so great that even the neutrons can no longer maintain their structure. This is where the quark matter phase comes into play. Quark stars are believed to be composed of quarks, the fundamental building blocks of protons and neutrons. In normal matter, quarks are bound together by the strong nuclear force, forming protons, neutrons, and other hadrons. But in the extreme conditions inside a quark star, the quarks themselves may become unbound, forming a hot, dense soup of free quarks. This is known as quark-gluon plasma, and it is thought to have existed in the early universe, just moments after the Big Bang. One of the most intriguing aspects of quark stars is the potential for them to be composed of strange quarks. In addition to the up and down quarks that make up protons and neutrons, there is a third type of quark called the strange quark. Strange quarks are thought to be more stable than the up and down quarks in certain high-energy environments, and they could form a new type of matter known as strange matter. Strange matter could exist in quark stars, making them even more exotic and difficult to study. If strange matter does indeed exist in quark stars, it could have profound implications for our understanding of the fundamental forces of nature and the behavior of matter at extreme densities. Despite the theoretical nature of quark stars, there are some observational clues that suggest they might exist. For instance, there have been several instances where astronomers have observed objects with masses that seem to fall into the range between neutron stars and black holes. These objects could be quark stars, although more data and observations are needed to confirm their existence. Additionally, the study of gravitational waves has opened up new possibilities for detecting quark stars. If these objects do exist, their interactions with other celestial bodies, such as neutron stars or black holes, could generate gravitational wave signals that we could detect here on Earth. One of the key challenges in studying quark stars is the difficulty in detecting them. These objects are likely to be incredibly small, dense, and faint, making them difficult to observe with traditional telescopes. However, recent advancements in observational techniques, such as the detection of gravitational waves, offer a new avenue for exploring the existence of quark stars. Gravitational waves are ripples in spacetime that are generated by the acceleration of massive objects, such as the merger of black holes or neutron stars. If quark stars are involved in such interactions, the resulting gravitational waves could carry valuable information about their properties, including their mass, spin, and structure. The detection of quark stars would not only be a groundbreaking discovery, but could also lead to significant advances in our understanding of the fundamental laws of physics. Quark stars offer a unique window into the behavior of matter under extreme conditions, and their study could help to refine our models of quantum mechanics, general relativity, and the strong nuclear force. Understanding the properties of quark stars could also help us understand the fate of the most massive stars in the universe, and the role they play in the formation of black holes and other exotic objects. In the coming years, we may be able to answer some of the most pressing questions about quark stars. Are they real objects, or merely theoretical constructs? How do they fit into the larger picture of stellar evolution? And what role do they play in the broader context of the universe? While much remains to be discovered, the quest to understand quark stars is sure to continue to push the boundaries of our knowledge and lead to new and exciting discoveries in the field of astrophysics. As our tools for exploring the cosmos become more advanced, we may find that quark stars are not as rare as we once thought. These exotic objects could be hiding in plain sight, waiting to be uncovered by the next generation of telescopes and gravitational wave detectors. Whether we find quark stars or not, the search for them will undoubtedly deepen our understanding of the universe and the fundamental forces that govern its behavior. The universe is full of mysteries, and quark stars represent just one of the many unsolved puzzles that await us. As we continue to explore the depths of space, we will undoubtedly encounter even more strange and fascinating objects that challenge our understanding of the cosmos. And in the process, we will continue to expand our knowledge of the forces that shape the universe and the fundamental nature of reality itself. The discovery of quark stars, or the confirmation of their existence, could be one of the most important breakthroughs in modern astrophysics, helping to unlock the secrets of the universe and revealing new insights into the nature of matter, energy, and space-time. Quark stars represent one of the most intriguing and mysterious objects in the universe. Existing between the well-known neutron stars and black holes, they offer a unique opportunity to study the behavior of matter under extreme conditions. Whether they are composed of strange quarks or quark-gluon plasma, quark stars could hold the key to understanding some of the deepest questions in modern physics. As we continue to explore the cosmos and develop new technologies, the search for quark stars will undoubtedly continue, and with it, the potential for groundbreaking discoveries that could change the way we understand the universe. The concept of quark stars not only pushes the boundaries of astrophysics, but also challenges our understanding of matter at its most fundamental level. The possibility of quark stars existing introduces a fascinating layer to the cosmic hierarchy, and their implications ripple through various scientific domains, from quantum mechanics to cosmology. As we delve deeper, we must consider the philosophical and practical ramifications of their existence. For one, quark stars compel us to question what we truly know about the life cycle of stars. If these exotic objects exist, then the standard model of stellar evolution would need to be revised to include this intermediate phase between neutron stars and black holes. It raises profound questions about how the universe operates on both macroscopic and subatomic scales. To understand this better, let's revisit the hypothetical process that could lead to the formation of a quark star. When a massive star reaches the end of its life, it explodes as a supernova, leaving behind a dense core. For less massive remnants, this core becomes a neutron star, supported by neutron degeneracy pressure, a quantum mechanical effect that prevents neutrons from occupying the same space. However, for larger remnants, the gravitational force may become so intense that even this degeneracy pressure is overcome. At this stage, the core could collapse further, and the neutrons themselves could decompose into their constituent quarks, leading to the formation of a quark star. This process involves unimaginable densities and temperatures. To put it into perspective, the density of a quark star would far exceed that of a neutron star, already one of the densest forms of matter in the universe. A single cubic centimeter of quark star material could weigh hundreds of millions of tons. At such densities, the usual rules of matter break down, and the behavior of quarks becomes the dominant factor. Understanding this state of matter is one of the greatest challenges in modern physics. Quark stars could also have unique properties that distinguish them from neutron stars and black holes. For example, their surface might be smoother than that of neutron stars due to the uniform distribution of quarks. They could also emit different types of radiation, making them potentially detectable by telescopes sensitive to specific wavelengths. Some theories suggest that quark stars might have extremely strong magnetic fields, even more powerful than those of neutron stars. These magnetic fields could influence the behavior of particles in the surrounding space, creating unique electromagnetic signatures. One particularly intriguing idea is that quark stars could emit bursts of energy in the form of gamma rays or other high-energy particles. These emissions could help scientists identify quark stars and distinguish them from other celestial objects. In fact, some observed gamma-ray bursts, which are among the most energetic phenomena in the universe, have been speculated to involve quark stars. These bursts might occur when two quark stars collide or when a neutron star transitions into a quark star. But the implications of quark stars extend far beyond their immediate properties. If strange matter exists in these stars, it could theoretically be stable even outside the extreme conditions of a quark star. This raises a fascinating possibility. Could strange matter play a role in the universe beyond quark stars? Some scientists have speculated that strange matter could, infect, ordinary matter, turning it into more strange matter. While this idea remains speculative, it underscores the potential for quark stars to revolutionize our understanding of matter. From a cosmological perspective, quark stars could also provide insights into the early universe. Shortly after the Big Bang, the universe was in an extremely hot and dense state, filled with a quark-gluon plasma. Studying quark stars could offer a glimpse into this primordial epoch, helping scientists understand the conditions that led to the formation of protons, neutrons, and other particles that make up the universe today. Furthermore, the discovery of quark stars would have profound implications for our understanding of black holes. If quark stars exist, they could represent a stage in the formation of black holes, bridging the gap between neutron stars and these enigmatic objects. This raises questions about the threshold conditions required for a quark star to collapse into a black hole and whether some quark stars could resist this collapse indefinitely. The search for quark stars is also driving advancements in observational technology. Telescopes and detectors capable of identifying the unique signatures of quark stars are becoming increasingly sophisticated. For instance, the detection of gravitational waves has opened a new window into the universe, allowing scientists to study the collisions of massive objects like neutron stars and black holes. If quark stars exist, their interactions could produce distinctive gravitational wave patterns that we could detect here on Earth. In addition to gravitational waves, other observational methods, such as X-ray and gamma-ray astronomy, could provide valuable clues. The study of pulsars, rapidly rotating neutron stars that emit beams of radiation, could also reveal the presence of quark stars. Some pulsars have unusual properties, such as extremely high rotational speeds or unexpected changes in their behavior, which could be explained by the presence of quark matter. As we continue to explore the universe, the potential discovery of quark stars represents a tantalizing possibility. These objects could fundamentally change our understanding of matter, energy, and the forces that govern the cosmos. They could also provide answers to some of the most profound questions in physics, such as the nature of the strong nuclear force and the behavior of matter under extreme conditions. At the same time, the study of quark stars highlights the interconnectedness of different scientific disciplines. From astrophysics to particle physics, the quest to understand these exotic objects requires a multidisciplinary approach. It also underscores the importance of collaboration and innovation in science. The discovery of quark stars, if it happens, will likely be the result of decades of research and the combined efforts of scientists around the world. The search for quark stars is not just about understanding a specific type of celestial object. It is about pushing the boundaries of human knowledge and exploring the fundamental nature of the universe. Whether or not quark stars exist, the journey to find them will undoubtedly lead to new discoveries and a deeper appreciation for the complexity and beauty of the cosmos. The universe is vast, mysterious, and full of surprises. Quark stars are a reminder of how much we still have to learn and how much there is to explore. They challenge us to think beyond the boundaries of what we know and to imagine new possibilities. And in doing so, they inspire us to keep asking questions and to never stop searching for answers. Quark stars, whether they remain theoretical or are eventually discovered, force us to confront some of the most fundamental questions about the universe. For example, if these stars exist, what does that tell us about the nature of matter and the boundaries of physical laws? How do they fit into the grand cosmic narrative, and what role might they play in the life cycles of galaxies or even the eventual fate of the universe? One possibility that intrigues scientists is the potential for quark stars to act as cosmic laboratories. These stars represent conditions that are impossible to replicate on Earth, densities billions of times greater than those found in the cores of neutron stars and temperatures so extreme that they defy conventional understanding. By studying quark stars, scientists could gain insights into the behavior of matter at its most extreme and fundamental level. This could, in turn, lead to breakthroughs in fields ranging from particle physics to nuclear engineering. Another fascinating avenue of research involves the potential for quark stars to help answer questions about dark matter. Dark matter is one of the great mysteries of modern astrophysics. It makes up about 27% of the universe's mass-energy content, yet it has never been directly observed. Some researchers speculate that strange quark matter could be a candidate for dark matter, or at least share properties that could shed light on its nature. If quark stars contain stable strange matter, they might offer clues about the elusive substance that influences the structure and behavior of galaxies. There is also the possibility that quark stars could play a role in the development of the universe's large-scale structure. Neutron stars and black holes are often found in binary systems, where they interact with other stars in complex ways. If quark stars exist, they too might be part of such systems, potentially leading to unique phenomena such as the merger of a quark star with another dense object. These interactions could produce gravitational waves, bursts of radiation, or other observable signals that might help scientists confirm the existence of quark stars and study their properties in detail. Moreover, quark stars could provide new insights into the ultimate limits of stellar collapse. Black holes represent one endpoint of stellar evolution, where gravity becomes so intense that even light cannot escape. However, if quark stars exist, they might represent a temporary halt in this collapse, a kind of pit stop on the way to forming a black hole. This raises the question, what determines whether a quark star collapses into a black hole? And what might this tell us about the fabric of spacetime itself? The study of quark stars also intersects with broader questions about the origins and fate of the universe. During the first moments after the Big Bang, the universe was a seething cauldron of quark-gluon plasma, a state of matter similar to what might exist inside a quark star. By studying these stars, scientists could gain a deeper understanding of this primordial state and the processes that led to the formation of the particles that make up the universe as we know it. On the other end of the cosmic timeline, quark stars might also have implications for the universe's ultimate fate. If quark matter is stable, it could persist even as other forms of matter decay over trillions of years. This raises the tantalizing possibility that quark stars, or remnants of them, could be among the last surviving objects in the cosmos, providing a kind of cosmic fossil record of the universe's history. Of course, all of this remains speculative until quark stars are definitively observed. But the search itself is a powerful reminder of humanity's drive to understand the unknown. From ancient astronomers gazing at the stars to modern scientists peering through sophisticated telescopes, the quest to unravel the mysteries of the cosmos is one of the defining endeavors of our species. The potential discovery of quark stars would not only expand our knowledge of the universe but also deepen our appreciation for its complexity and wonder. These enigmatic objects, if they exist, are a testament to the infinite possibilities that lie beyond the limits of our current understanding. They remind us that the universe is a place of endless discovery, filled with phenomena that challenge our imaginations and inspire us to keep exploring. As we continue to develop new technologies and refine our theories, the search for quark stars will remain at the forefront of astrophysical research. It is a journey that requires not only scientific ingenuity, but also a profound sense of curiosity and wonder. And it is a journey that has the potential to transform our understanding of the universe in ways we can scarcely imagine. Quark stars are more than just a theoretical possibility. They are a symbol of the unknown, a reminder that the universe is far more complex and fascinating than we can ever fully comprehend. They challenge us to think beyond the boundaries of what we know and to embrace the mysteries that lie at the heart of existence. Quark stars also push the boundaries of our philosophical understanding of the universe. If they exist, they serve as a reminder that even the most extreme phenomena in the cosmos often follow rules and patterns that are waiting to be uncovered. They represent a form of cosmic elegance, where the chaos of immense gravitational forces and unimaginable densities gives way to a strange and orderly state of matter. The very idea of quark stars challenges us to consider the limits of natural laws and how much more there is to learn about the universe's hidden mechanisms. One of the most intriguing aspects of quark stars is their potential role as intermediaries between neutron stars and black holes. In a sense, they may represent the missing link in the stellar life cycle, filling a gap in our understanding of what happens when massive stars die. But this raises deeper questions. How common are quark stars? Are they rare exceptions, or could there be vast populations of these objects hiding in plain sight? The challenge of detecting quark stars lies in their similarities to neutron stars and black holes, but their distinct characteristics, such as unique radiation emissions or gravitational wave signatures, might one day allow us to identify them conclusively. Furthermore, the study of quark stars could fundamentally alter our understanding of how matter transitions from one state to another. Scientists believe that quark matter may exist in various forms, depending on factors such as density and temperature. If quark stars are composed of strange quark matter or a mix of different quarks, they might exhibit properties that differ significantly from what we observe in neutron stars. These differences could provide insights into the physics of phase transitions, helping us understand how matter behaves under extreme conditions, not just in the cosmos but also in particle accelerators on Earth. The search for quark stars also intersects with advancements in observational astronomy. Instruments like the Laser Interferometer Gravitational Wave Observatory, LIGO, and the Event Horizon Telescope, EHT, have already transformed our ability to study compact objects like neutron stars and black holes. These tools could play a crucial role in identifying quark stars by detecting the unique signatures they might produce during mergers or other high-energy events. For example, a collision involving a quark star could produce gravitational waves with patterns distinct from those generated by neutron star or black hole mergers. Such observations would provide a treasure trove of data for astrophysicists, helping to confirm or refute the existence of these enigmatic objects. Another fascinating angle involves the potential use of quark stars as natural laboratories for studying the forces that govern the universe. Quarks are held together by the strong nuclear force, one of the four fundamental forces of nature. This force is responsible for binding protons and neutrons in atomic nuclei, but it operates on scales that are incredibly difficult to study directly. Quark stars, however, might offer a macroscopic glimpse into the behavior of the strong nuclear force under extreme conditions. By studying the radiation emitted by quark stars or the gravitational waves they generate, scientists could gain new insights into this powerful and poorly understood force. Quark stars might also play a role in understanding the universe's energy balance. These objects could act as reservoirs of energy, storing vast amounts of potential energy within their dense cores. If strange quark matter is indeed stable, it might even be possible for quark stars to release energy in ways that differ from traditional stellar processes. This has led to speculative discussions about whether quark stars could one day be harnessed as a source of energy, though such ideas remain firmly in the realm of science fiction for now. From a cosmological perspective, quark stars may offer clues about the universe's early moments. The conditions inside a quark star are thought to resemble those that existed microseconds after the Big Bang, when quarks and gluons roamed freely before coalescing into protons and neutrons. Studying quark stars could thus provide a window into this primordial era, helping scientists test theories about the universe's birth and the fundamental processes that shaped its evolution. In addition, quark stars might help answer one of the most profound questions in astrophysics. What is the ultimate fate of matter? As stars age and die, they leave behind remnants that can take the form of white dwarfs, neutron stars, or black holes. Quark stars, if they exist, represent another possible endpoint in this process. But what happens to quark stars over billions or trillions of years? Do they remain stable indefinitely, or do they eventually decay into simpler forms of matter? Understanding the long-term evolution of quark stars could shed light on the destiny of matter in a universe that continues to expand and cool over time. The search for quark stars is also deeply interconnected with the study of other cosmic phenomena, such as gamma-ray bursts and fast radio bursts. These high-energy events, which remain poorly understood, might involve quark stars in ways that have yet to be uncovered. For example, a quark star transitioning into a black hole could produce a burst of radiation with unique characteristics, providing a potential observational signature of these elusive objects. Ultimately, the study of quark stars is about more than just understanding a specific type of star. It is a quest to explore the fundamental nature of reality, to push the boundaries of human knowledge, and to uncover the secrets of the universe's most extreme environments. Whether or not quark stars are ever definitively identified, the pursuit of this knowledge enriches our understanding of the cosmos and inspires new generations of scientists to continue asking bold questions. The role of quark stars in the universe is still a mystery, but it is a mystery that captures the imagination and challenges our understanding of the cosmos. These objects, if they exist, could hold the key to answering some of the most profound questions about the nature of matter, the limits of physical laws, and the ultimate fate of the universe itself. In the end, quark stars remind us that the universe is far more complex and wondrous than we can ever fully comprehend, and that the journey to understand it is one of the greatest adventures of all. The pursuit of quark stars, in many ways, embodies humanity's relentless curiosity and determination to uncover the unknown. Even without direct evidence of their existence, the very act of exploring the theoretical possibility of these exotic objects has already yielded profound insights into physics, cosmology, and the intricate workings of the universe. Every question about quark stars opens the door to a cascade of new inquiries, leading to a deeper understanding of both the cosmos and our place within it. One of the most tantalizing aspects of quark stars lies in their potential to redefine the boundaries of stellar evolution. Stars, in their various forms, are among the most studied objects in the universe. From the relatively simple main-sequence stars like our Sun to the enigmatic neutron stars and massive black holes, we've developed a robust framework to classify and understand these celestial bodies. Yet, quark stars challenge this framework, potentially adding an entirely new category to the stellar evolutionary tree. In this context, quark stars might serve as a transitional phase, existing in the delicate balance between the degeneracy pressure of quark matter and the overwhelming gravitational force trying to compress the star further. This equilibrium could provide scientists with a snapshot of how matter behaves at the very edge of collapse, a phenomenon that could bridge the gap in our understanding of how black holes form and what lies just before the event horizon. Quark stars may also hold implications for understanding the universe's energy dynamics. Their formation would require processes involving extreme gravitational and thermal interactions, potentially releasing unique forms of energy. These energy outputs might manifest as rare and powerful astrophysical events that have been observed but remain unexplained. For instance, gamma-ray bursts and fast radio bursts are some of the most energetic phenomena in the universe, yet their origins are still hotly debated. Could the sudden collapse of a neutron star into a quark star, or the merger of a quark star with another dense object, be responsible for these bursts? Theoretical models suggest that such events could produce distinct energy signatures, offering a potential avenue for identifying quark stars indirectly. Another fascinating prospect is the possibility that quark stars might not be isolated phenomena but could form in clusters or even interact with one another. Dense regions of space, such as globular clusters or galactic cores, are home to high concentrations of stars, some of which evolve into neutron stars or black holes. If quark stars exist, these environments might harbor them as well, potentially leading to unique interactions. For example, Two quark stars in a binary system could emit gravitational waves with a signature distinct from those of neutron star mergers. Detecting such signals would provide compelling evidence for the existence of quark stars and shed light on their properties. Theoretical physicists are also exploring the idea that quark stars could evolve over time, undergoing transitions that alter their internal structure and composition. For example, a quark star might begin as a strange quark star, composed primarily of strange quarks, but gradually transition to a state dominated by up and down quarks as conditions inside the star change. These transitions could have observable effects, such as fluctuations in the star's luminosity or periodic emissions of radiation, providing potential clues for astronomers searching for these elusive objects. Quark stars also have intriguing implications for the study of compact star collisions. When neutron stars collide, they produce gravitational waves and bursts of electromagnetic radiation, as observed in the groundbreaking 2017 event GW170817. If one or both of the colliding objects were quark stars, the resulting signals would likely differ in subtle but measurable ways. For instance, the gravitational waveforms might reveal information about the star's internal structure, such as the presence of quark matter. These differences could provide indirect evidence for the existence of quark stars and offer a new perspective on the dynamics of compact object mergers. The potential role of quark stars in galactic evolution is another area of interest. Galaxies are shaped not only by their stars but also by the remnants left behind when stars die. If quark stars exist, they could contribute to the population of compact objects that influence a galaxy's gravitational dynamics and star formation processes. Over time, quark stars might migrate toward the center of their host galaxy, joining the dense environment near the supermassive black hole that resides there. This could lead to interactions with other compact objects, creating a dynamic and complex ecosystem that shapes the galaxy's evolution in ways we have yet to understand. From a more speculative perspective, quark stars could even play a role in the search for extraterrestrial life. While this might seem far-fetched, consider that the study of exotic objects like quark stars often leads to unexpected discoveries with far-reaching implications. For example, understanding the conditions that give rise to quark matter might shed light on the behavior of matter in extreme environments, such as those found on exoplanets orbiting neutron stars or quark stars. These insights could inform our search for life in the universe, particularly in places where conditions are vastly different from those on Earth. The exploration of quark stars also serves as a reminder of the interconnectedness of scientific discovery. Advances in one field often lead to breakthroughs in others, creating a ripple effect that pushes the boundaries of human knowledge. Theoretical models of quark stars, for instance, have already contributed to our understanding of quantum chromodynamics, the theory that describes the strong nuclear force. Similarly, the search for quark stars has driven the development of advanced observational techniques, such as high-sensitivity detectors for gravitational waves and electromagnetic radiation. At its core, the study of quark stars is a testament to the power of human curiosity. These objects, if they exist, represent some of the most extreme and mysterious phenomena in the universe. Yet, they also embody the idea that even the most seemingly esoteric questions can lead to profound insights about the nature of reality. By pursuing the mystery of quark stars, scientists are not only seeking to expand our understanding of the cosmos, but also exploring the very limits of what is possible in the universe. Quark stars, with their strange and exotic properties, challenge us to think beyond the familiar and to embrace the unknown. They remind us that the universe is a place of endless wonder, filled with mysteries that defy easy explanation. And they inspire us to continue asking questions, pushing the boundaries of what we know, and seeking answers to the deepest mysteries of existence. Quark stars, though still theoretical, highlight the vastness of our ignorance and the astonishing potential for discovery in astrophysics. The implications of their existence reach far beyond the confines of stellar evolution or theoretical physics. They invite us to reconsider how we understand the fundamental nature of matter and energy. To explore these enigmatic objects is to push the limits of human knowledge, demanding new frameworks of thought and innovative methods of observation. But just as their potential is vast, so too are the challenges involved in confirming their existence. One of the central difficulties lies in the extreme nature of the conditions that would create a quark star. These stars, if they exist, would be formed under the most extreme pressures and temperatures, far surpassing anything we can replicate on Earth. For instance, a quark star would likely be born from the collapse of a massive neutron star, where the pressures are so intense that even the neutrons themselves break apart into their constituent quarks. This process requires conditions that are difficult to simulate, let alone observe directly, making the discovery of quark stars a formidable challenge. Theories of quark stars are largely based on our understanding of the strong nuclear force, which binds quarks together in protons and neutrons. In the core of a quark star, these quarks could exist in a free state, held together not by the usual nuclear forces but by a much stronger and denser form of quark matter. This would result in a star whose internal structure is radically different from that of a traditional neutron star. However, because this state of matter has never been directly observed, scientists must rely on complex models and simulations to predict how quark stars might behave. Furthermore, the detection of quark stars is complicated by their potential similarity to neutron stars. Both types of stars are extremely dense, and their behavior might appear strikingly similar, especially in terms of gravitational waves, electromagnetic radiation, and other observables. This makes it difficult to distinguish between the two, and as of now, there is no definitive way to identify a quark star based solely on the available data. In fact, even if quark stars were common in the universe, we might still struggle to detect them, as their signatures could be subtle and easily overshadowed by the more familiar signals from neutron stars or black holes. Despite these challenges, there are several promising approaches that could lead to the discovery of quark stars. One of the most exciting avenues is the detection of gravitational waves. When compact objects like neutron stars or black holes collide, they release powerful ripples in spacetime, which can be detected by observatories like LIGO and Virgo. If quark stars exist, their mergers might produce gravitational waves with distinct characteristics that could set them apart from other events. These waves might contain information about the star's internal structure and the nature of the matter within it, offering a clue to their existence. Another potential method of detecting quark stars involves the study of their electromagnetic emissions. Just as neutron stars emit X-rays and gamma rays as a result of their extreme environments, quark stars might produce similar radiation, but with subtle differences. For instance, quark stars might emit high-energy photons in bursts, or in a pattern that is unlike anything seen from other celestial objects. By observing these emissions with telescopes like the Chandra X-ray Observatory or the upcoming James Webb Space Telescope, astronomers might be able to detect the presence of quark stars indirectly. Additionally, as our observational techniques improve, we may find new ways to look for quark stars within the dense environments of star clusters or the centers of galaxies. These regions are known to harbor compact objects, and if quark stars exist, they might be among the most intriguing objects to observe. The presence of a quark star in such an environment could influence the surrounding stellar dynamics, potentially providing further evidence of their existence. Yet even as we develop more sophisticated methods of observation, we must acknowledge that the search for quark stars may not yield immediate results. The universe is vast, and the conditions necessary for the formation of quark stars are exceedingly rare. Moreover, the nature of these objects may be so alien to our understanding that we might not even recognize their signatures when we see them. Just as astronomers once had no idea that black holes existed until the late 20th century, we may be on the verge of discovering a new class of stars that are just as strange and elusive. The existence of quark stars could also reshape our understanding of the fate of the universe itself. If quark stars are real, they would represent a new stage in the life cycle of matter under extreme conditions. As our universe evolves, the role of such stars could be pivotal in the formation of black holes, the recycling of cosmic material, and the eventual death of galaxies. Quark stars might even provide insights into the ultimate fate of the universe, helping to answer questions about dark energy, the expansion of the cosmos, and the fundamental forces that govern everything from subatomic particles to the largest structures in the universe. In the grand scheme of things, Quark stars may not only serve as cosmic curiosities but could provide a window into the very nature of reality itself. What happens at the heart of a quark star? What forces are at play inside its core? And what do these stars reveal about the fundamental structure of matter and the universe as a whole? These questions are the very essence of what drives scientific inquiry, and the answers to them could have profound implications for our understanding of everything from quantum mechanics to general relativity. As we continue to explore the mysteries of quark stars, we also find ourselves faced with a broader philosophical question: what does it mean to understand the universe? In many ways, the study of objects like quark stars forces us to confront the limits of human knowledge. The universe is so vast and complex, with phenomena far beyond our ability to directly observe or fully comprehend. Yet, through careful observation, theoretical modeling, and scientific experimentation, we have made incredible strides in understanding the cosmos. Quark stars represent the next frontier in this exploration, a challenge that will require the best minds in science to crack open. What we do know, however, is that the discovery of quark stars would open up a new chapter in the history of astrophysics. They would stand as testament to the power of human curiosity and the relentless drive to uncover the deepest truths about the universe. Whether or not they exist, the search for quark stars exemplifies the spirit of scientific inquiry, the willingness to ask the hard questions, to challenge accepted paradigms, and to explore the unknown. In the future, when we look back on this period of discovery, we may find that quark stars were one of the most important stepping stones in our understanding of the universe. Or perhaps, they will remain an elusive mystery, one of many enigmas in the cosmos that continues to beckon us toward new discoveries, new theories, and new frontiers of knowledge. As we continue to expand our understanding of the cosmos, the role of quark stars might prove to be one of the most intriguing pieces of the puzzle. In many ways, the pursuit of answers about quark stars reflects the broader human quest for knowledge, pushing us beyond the confines of our current limitations and challenging everything we thought we knew about the universe. The challenge in detecting quark stars is not just a technological one, it's also a conceptual one. After all, the idea of quark matter existing in a stable, large-scale form is a radical departure from the conventional understanding of matter as we know it. If quark stars exist, it would challenge some of the foundational principles of physics that have stood for centuries. It would mean that matter, under extreme conditions, can behave in ways that are completely foreign to our everyday experiences. Imagine, for a moment, what such a discovery would mean for the fields of both astrophysics and quantum mechanics. In a quark star, we would not be observing the traditional structure of matter, protons and neutrons bound together by the strong force. Instead, we would be looking at a state where quarks themselves, the fundamental building blocks of matter, are free to move independently in a dense, highly compressed state. The physics behind quark stars would require new models that integrate quantum chromodynamics, the theory that describes the interactions between quarks, with the principles of general relativity. These two fields of physics have historically been difficult to reconcile, but quark stars might serve as the missing link that finally brings them together in a unified theory of quantum gravity. Moreover, if quark stars are found, they could help us address some of the most fundamental questions about the nature of the universe. For example, how did the universe come to be, and what is the true fate of stars that die in the most violent explosions? Quark stars could serve as a crucial piece in understanding the life cycle of stars. They might represent an intermediate state between neutron stars and black holes, suggesting a smooth transition in the evolution of stellar remnants under extreme conditions. Perhaps, at the core of some massive supernova remnants, quark stars are waiting to be discovered, their extreme density and exotic composition hiding in plain sight. Quark stars could also have important implications for understanding the nature of dark matter. While dark matter has yet to be directly detected, it is believed to make up a significant portion of the universe's mass. One possibility is that quark stars could contribute to this mysterious substance. If quark matter is indeed stable and exists in the form of quark stars, then these objects might represent a significant portion of the universe's invisible mass. In this sense, quark stars could bridge the gap between the visible and invisible components of the cosmos, offering a new way to think about the makeup of the universe and its unseen forces. The search for quark stars will likely continue to push the boundaries of observational technology. As new space telescopes and ground-based observatories come online, we may have more tools to observe the most distant and extreme corners of the universe. Instruments like the upcoming James Webb Space Telescope or the European Space Agency's Athena X-ray Observatory could offer the sensitivity required to detect the faint signals that might point to quark stars. However, even with these advanced instruments, the challenge will be in interpreting the data. Without a clear understanding of what a quark star might look like, every observation could present more questions than answers. This will require collaboration between theorists, observational astronomers, and experimental physicists, who will need to work together to develop new models and predictions based on the data. In the quest for quark stars, one of the key observations to watch for is how these objects might interact with their environment. Because quark stars would likely be incredibly dense, they could have strong magnetic fields and could influence their surroundings in ways that are distinct from neutron stars or black holes. Perhaps quark stars might behave as strange attractors, drawing in matter from nearby stars or interstellar gas clouds. This could produce electromagnetic radiation in the form of X-rays or gamma rays, providing further clues about their composition and behavior. If quark stars have strong magnetic fields, they might even produce bursts of radiation, similar to the phenomena observed in pulsars, but with differences that are specific to their unique composition. Moreover, the study of quark stars could also open the door to new areas of research in high-energy physics. The conditions inside a quark star would likely be unlike anything we can replicate on Earth, making them a natural laboratory for understanding the behavior of matter under extreme pressure and temperature. These objects could provide insights into the behavior of quarks, gluons, and other subatomic particles in ways that current particle accelerators cannot. In particular, quark stars might offer a glimpse into the physics of the strong force, a fundamental force of nature that governs the interactions between quarks. By studying the interactions between quarks in these extreme environments, scientists could gain a better understanding of the fundamental laws of physics. One of the most intriguing aspects of quark stars is that they may not be a singular phenomenon in the universe. If they exist, quark stars could potentially be scattered throughout the cosmos, lurking in the same regions where neutron stars are found. It's possible that there are quark stars that have yet to be discovered simply because they are indistinguishable from neutron stars in the data we have so far. This could mean that the universe is home to many more of these exotic objects than we realize. However, as long as quark stars remain theoretical, their existence will continue to be a subject of debate among scientists. The search for them will undoubtedly remain a challenging and exciting frontier in astrophysics, with the potential to uncover new forms of matter and new insights into the evolution of stars and the universe itself. In the coming decades, as the quest for quark stars progresses, we may see groundbreaking discoveries that change our understanding of the universe. If we do find conclusive evidence for the existence of quark stars, it will be one of the most significant moments in the history of science. This discovery could spark a wave of new research into the nature of matter, the life cycle of stars, and the fundamental forces that govern the cosmos. It might also lead to unexpected breakthroughs in other areas of physics, as scientists continue to investigate the bizarre and fascinating properties of quark stars. Ultimately, whether or not quark stars exist, their study will undoubtedly contribute to the broader field of astrophysics, helping us better understand the universe and our place within it. The search for these strange and elusive objects will challenge our ideas about matter, energy, and the very fabric of reality, pushing the boundaries of science in ways that we are only beginning to imagine. The quest to understand quark stars is more than just a search for a theoretical object. It's a journey that could redefine our view of the universe. As we explore the possibility of their existence, it becomes clear that their discovery could unlock some of the most profound mysteries of the cosmos. These exotic objects could hold the key to understanding the most extreme conditions in the universe, places where gravity, pressure, and temperature push the laws of physics to their limits. While the idea of quark stars has captivated the imagination of many astrophysicists, it's important to remember that these stars represent a hypothetical state of matter, one that has yet to be conclusively observed. The nature of quark matter remains one of the most difficult questions in modern physics. For decades, scientists have attempted to simulate and understand quark-gluon plasma, a state of matter that is thought to exist at the core of quark stars, in particle accelerators. Yet, despite our advancements in high-energy particle physics, the environment inside a quark star is so extreme that recreating it on Earth remains beyond our current capabilities. But even though we can't yet create the conditions necessary to observe quark stars directly, there are still ways to test their existence. One promising avenue of exploration lies in the study of gravitational waves. These ripples in spacetime, caused by massive objects accelerating through the universe, have already opened up new possibilities for observing some of the most violent events in the cosmos. The detection of gravitational waves from neutron star mergers, for example, has provided valuable insight into the nature of these objects. It's possible that, in the future, we may detect gravitational waves from quark star mergers, offering direct evidence of their existence. Furthermore, the study of compact objects like neutron stars and black holes may provide indirect evidence for quark stars. When a neutron star undergoes a supernova explosion, for instance, it may collapse into a quark star before eventually becoming a black hole. If such a process occurs, it could leave behind observable remnants that could reveal the existence of quark stars. Similarly, the way in which neutron stars behave in binary systems could provide clues about the presence of quark matter. In systems where a neutron star interacts with a companion star, the exchange of material between the two objects might cause the neutron star to undergo an intense transformation, potentially leading to the formation of a quark star. By studying the behavior of such systems, we may be able to uncover the fingerprints of quark stars in the data. But even if quark stars are never directly observed, their theoretical implications remain profound. They could reshape our understanding of the fundamental forces at play in the universe. In particular, quark stars challenge our conventional understanding of the strong force, the fundamental interaction that binds quarks together to form protons and neutrons. At present, the strong force is described by quantum chromodynamics (QCD), but this theory breaks down at the extreme conditions found inside quark stars. If quark stars do exist, they could provide a real-world laboratory for studying QCD in ways that are not possible with current experimental methods. This could lead to a deeper understanding of the strong force, helping to refine our theories of particle physics and perhaps even leading to the development of new theories that unify the fundamental forces of nature. Another potential impact of the discovery of quark stars is the insight they could offer into the nature of the early universe. During the first moments after the Big Bang, the universe was filled with extremely hot, dense matter, and quarks were free to move independently in a state known as quark-gluon plasma. As the universe cooled, quarks combined to form protons and neutrons, which eventually led to the formation of atoms, stars, and galaxies. If quark stars do exist, they could represent a remnant of this primordial state of matter, offering a glimpse into the conditions that existed during the infancy of the universe. Understanding the properties of quark stars could, therefore, help us unravel the mysteries of the early cosmos, providing clues about the processes that led to the formation of the universe as we know it. The study of quark stars could also have practical implications for our understanding of the extreme environments that exist in the universe. For example, quark stars may offer a new perspective on the behavior of matter under extreme pressure. In the cores of stars, pressures and temperatures are already incredibly high, but quark stars represent an even more extreme environment. By studying how matter behaves in these conditions, scientists could gain valuable insights into materials science, particularly in understanding how matter behaves under extreme stress. This could have applications in fields ranging from nuclear physics to materials engineering, where the principles of extreme pressure are often applied in technologies like nuclear reactors or particle accelerators. Additionally, the discovery of quark stars could have implications for our understanding of the nature of black holes. As mentioned earlier, quark stars are thought to exist between neutron stars and black holes, potentially serving as an intermediate state in the collapse of a star. If this is the case, then studying quark stars could help us better understand how black holes form and what happens to matter as it collapses into a singularity. This could lead to new insights into one of the most enigmatic objects in the universe, potentially bringing us closer to understanding the nature of black holes and the mysteries surrounding them. Even without a direct observation of quark stars, the theoretical models that predict their existence are pushing the boundaries of our understanding of matter, energy, and gravity. The mathematics behind these models involves advanced concepts like quantum chromodynamics, relativistic fluid dynamics, and high-energy astrophysics, which are at the forefront of modern physics. As these models evolve and new data becomes available, scientists are likely to continue refining their predictions and improving our understanding of the conditions that lead to the formation of quark stars. This process of continuous refinement and testing is how scientific progress is made, and it is likely that the search for quark stars will lead to new discoveries that extend far beyond this specific question. The mystery of quark stars serves as a powerful reminder of how much there is still to learn about the universe. These exotic objects challenge our understanding of matter, energy, and the fundamental forces that govern the cosmos. Whether or not quark stars are eventually discovered, the quest to find them will undoubtedly shape the future of astrophysics, particle physics, and our broader understanding of the universe. The search for quark stars is not just a scientific endeavor. It is a journey of exploration that could illuminate some of the deepest secrets of the cosmos. The search for quark stars holds the potential to answer some of the most profound questions about the nature of matter and the universe itself. As we continue to probe the mysteries of the cosmos, it is important to acknowledge that quark stars may not be the only exotic objects waiting to be discovered. Just as the universe is vast, so too is the range of phenomena that may exist between the familiar objects we know, like black holes and neutron stars, and the unknown. Quark stars are just one piece of this cosmic puzzle, but their discovery could pave the way for a deeper understanding of the fundamental nature of space, time, and matter. One of the key aspects of quark stars is the role they play in the context of stellar evolution. Traditional stellar evolution theories typically describe how a star forms, lives, and ultimately ends its life as a white dwarf, neutron star, or black hole. However, quark stars introduce a new layer of complexity to this narrative. If they are indeed a real phenomenon, quark stars would represent a transitional phase between the dense, compact nature of neutron stars and the complete gravitational collapse that leads to black holes. This transition could have significant implications for our understanding of how stars end their lives and what happens to the matter within them as they undergo these extreme transformations. Furthermore, the presence of quark stars would challenge existing models of star formation and collapse. Current theories suggest that when a star reaches the end of its life, it will either explode as a supernova or collapse under its own gravity, forming a neutron star or black hole. The idea of a quark star existing between these two states suggests that there may be additional steps or stages in the life cycle of massive stars. This idea would necessitate a reevaluation of how we understand the processes that govern stellar death and the subsequent formation of compact objects like neutron stars and black holes. It could also provide new insights into the physics of supernovae, which are some of the most powerful and energetic events in the universe. Another area where quark stars could have a profound impact is in our understanding of the fundamental forces of nature. As previously mentioned, the strong force is responsible for holding quarks together to form protons and neutrons, and it is the force that dominates inside quark stars. While the theory of quantum chromodynamics, QCD, provides a framework for understanding the behavior of quarks and the strong force, it is still an incomplete theory, particularly when it comes to understanding how quarks behave under the extreme conditions found inside quark stars. If quark stars exist, they could offer a unique environment in which to test QCD in ways that are not possible in other settings. The discovery of quark stars could also lead to a deeper understanding of the relationship between gravity and quantum mechanics. These two fundamental forces of nature, gravity and the strong nuclear force, have proven difficult to reconcile within a single unified theory. While general relativity successfully describes the behavior of gravity on large scales, it does not incorporate quantum mechanics, which governs the behavior of particles on the smallest scales. Quark stars, with their extreme density and unique properties, could provide a testing ground for new theories that attempt to unify these two forces, offering insights into the quantum nature of gravity and the potential for a theory of quantum gravity. In addition to advancing our understanding of fundamental physics, the study of quark stars could have implications for other areas of astrophysics. For instance, quark stars could offer new insights into the behavior of matter under extreme gravitational conditions. Their existence could have implications for our understanding of gravitational waves, a relatively new field of study that has already provided groundbreaking results. By studying how quark stars might behave in gravitational wave experiments, scientists could gain valuable information about the nature of these objects and their role in the universe. Additionally, if quark stars are found to emit gravitational waves during collisions or mergers, they could provide a new source of information about the nature of compact objects in the cosmos. Another exciting aspect of quark stars is their potential connection to dark matter. Dark matter remains one of the biggest unsolved mysteries in astrophysics. While we can't observe dark matter directly, its presence is inferred through its gravitational effects on visible matter. Some scientists have proposed that quark stars could be a candidate for dark matter, as they are composed of a type of matter that is not easily detectable through conventional means. If quark stars do exist and have properties that make them difficult to observe, they could contribute to the invisible mass that makes up dark matter. This connection would open up new avenues for research into the nature of dark matter and potentially bring us closer to solving one of the most fundamental puzzles in modern physics. The possibility of quark stars could also provide valuable insights into the structure and evolution of galaxies. Most galaxies, including our own Milky Way, are thought to contain supermassive black holes at their centers. These black holes are believed to play a crucial role in the formation and evolution of galaxies, influencing the growth of stars, the distribution of matter, and the overall dynamics of the galaxy. If quark stars exist, they could offer a new perspective on the role of compact objects in galaxy formation and evolution. For example, quark stars could potentially serve as a bridge between the formation of neutron stars and the growth of supermassive black holes, helping to clarify how these objects interact and influence the surrounding galactic environment. Even if quark stars do not turn out to be a significant component of the universe, the very process of searching for them will undoubtedly lead to new discoveries and insights. The tools and techniques that scientists develop to study these objects, such as advanced telescopes, gravitational wave detectors, and high-energy particle accelerators, will likely yield new findings that push the boundaries of human knowledge. Just as the study of neutron stars, black holes, and other cosmic phenomena has led to groundbreaking discoveries in physics and astronomy, the pursuit of quark stars could open up entirely new areas of research that will shape our understanding of the universe for generations to come. The mystery of quark stars is more than just a scientific curiosity. It's a window into the deepest questions about the nature of reality. These exotic objects challenge our understanding of matter, energy, and the fundamental forces of nature, and their discovery could have profound implications for fields ranging from astrophysics to particle physics. As we continue to explore the cosmos, we are reminded of the vastness of the universe and the endless possibilities for discovery. Whether or not quark stars exist, the pursuit of answers will undoubtedly lead to new and exciting revelations that will expand our understanding of the universe and our place within it. The implications of quark stars extend beyond the scientific community and have the potential to redefine how we approach questions about the universe itself. If quark stars do exist, their discovery would undoubtedly shift the conversation around stellar formation, gravitational physics, and quantum mechanics. It would represent a milestone in our quest to understand the most extreme conditions the universe has to offer. Understanding the formation, properties, and potential role of quark stars could also illuminate other cosmic phenomena, leading to the discovery of new types of celestial objects or unusual events that have eluded us thus far. One of the most intriguing aspects of quark stars lies in their potential relationship to black holes. These enigmatic objects are often considered the end state for massive stars, where matter collapses so completely that not even light can escape. However, the concept of a quark star suggests that there may be an intermediary state between neutron stars, dense objects made of neutrons packed tightly together, and black holes, which are considered to be the ultimate collapse. A quark star could be a celestial object where the matter is more compact than a neutron star but hasn't yet undergone the complete collapse to form a black hole. Understanding this intermediate phase could give us key insights into the processes of gravitational collapse. This knowledge would help us answer critical questions about the limits of matter, the nature of spacetime near extreme gravitational fields, and the forces that drive stellar death. The existence of quark stars would also provide a better understanding of the boundary between the dense yet observable states of matter and the hidden singularity that lies at the heart of black holes. This boundary is one of the central mysteries in theoretical physics, and understanding quark stars could offer a rare glimpse into how nature pushes matter to its breaking point. Another critical aspect of quark stars is how they could contribute to our understanding of the early universe. We know that the universe began in a highly energetic state, with particles and matter in extreme forms. The quark-gluon plasma, a state of matter believed to have existed just moments after the Big Bang, is thought to have consisted of free quarks and gluons, particles that would eventually combine to form protons, neutrons, and other building blocks of matter. If quark stars do exist, they could provide a link between this primordial state of matter and the matter we observe in the universe today. By studying quark stars, scientists could potentially gain insight into the conditions of the early universe, offering a window into a time long before galaxies, stars, or even atoms existed. Additionally, quark stars could provide valuable clues about the limits of matter and the behavior of quarks under extreme conditions. The idea that matter can exist in a state where quarks are no longer confined within protons and neutrons is revolutionary, as it challenges our traditional understanding of how matter is structured. For many decades, physicists have believed that quarks could never exist freely, outside of the protons and neutrons they typically form. However, the possibility of quark stars suggests that under certain conditions, such as the immense pressure and density found inside these stars, quarks could break free of their usual confines and form a new state of matter. Studying this phenomenon could offer new insights into the fundamental building blocks of the universe, shedding light on the forces that govern their interactions. The discovery of quark stars could also have far-reaching implications for the study of quantum mechanics. Currently, one of the major challenges in physics is reconciling quantum mechanics, which governs the behavior of particles at the smallest scales, with general relativity, which describes the behavior of gravity on cosmic scales. The study of quark stars could provide a unique environment for testing new theories that attempt to merge these two domains. For example, if quark stars are found to behave in ways that challenge our current understanding of gravity and quantum theory, it could lead to the development of a more unified theory of physics, one that successfully incorporates both the quantum world and the cosmos. In addition, quark stars may offer a novel approach to understanding gravitational waves, another phenomenon that has garnered widespread interest in recent years. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as the collision of black holes or neutron stars. These waves were first detected in 2015 by the LIGO, Laser Interferometer Gravitational Wave Observatory, collaboration, marking a major breakthrough in astrophysics. Since then, scientists have been keen to understand how different types of compact objects, such as neutron stars, black holes, and potentially quark stars, emit gravitational waves during interactions. If quark stars exist, their mergers or collisions could produce distinct gravitational wave signatures that might help scientists differentiate them from other objects in the universe. This would allow for a more precise understanding of the properties of quark stars and further enrich our knowledge of the complex behavior of compact objects. Moreover, studying how quark stars interact with other objects in space could lead to new methods of detecting these elusive objects, providing valuable insights into their role within the broader cosmic landscape. Interestingly, the properties of quark stars could also have implications for the study of dark energy, the mysterious force that is causing the accelerated expansion of the universe. While dark energy is still poorly understood, the existence of quark stars may offer new clues about the underlying mechanisms driving the universe's expansion. Some researchers have suggested that the behavior of matter under extreme conditions, such as those found within quark stars, could be linked to the forces that influence the large-scale structure of the cosmos. If this connection proves to be true, quark stars could become a key piece of the puzzle in understanding dark energy and its role in the universe's evolution. As we continue to explore the possibility of quark stars, it is important to remember that these objects represent just one facet of the incredible complexity of the universe. Our quest to understand the cosmos is far from complete, and quark stars may be just the tip of the iceberg when it comes to discovering new, exotic forms of matter. While the idea of quark stars may sound otherworldly or fantastical, it is grounded in the latest advances in astrophysics and particle physics. If they do exist, quark stars would challenge our conventional understanding of matter, gravity, and the fundamental forces that shape the universe. Whether or not they ultimately prove to be real, the pursuit of knowledge about these objects will undoubtedly lead to new discoveries and further our understanding of the universe in ways we have yet to imagine. Exploring the existence and properties of quark stars also presents an intriguing challenge for observational astronomy. As we continue to study the cosmos, the search for these enigmatic objects will require innovative techniques and the development of cutting-edge technology. Traditional methods of observing distant stars and stellar remnants, such as optical telescopes and X-ray observatories, may not be enough to detect quark stars due to their unique and extreme properties. For example, the extreme density and gravitational forces surrounding a quark star could prevent us from observing it in the same way we observe more familiar objects like black holes or neutron stars. To detect quark stars, astronomers would need to rely on indirect methods, similar to the techniques used to study black holes and other compact objects. One promising approach involves the detection of gravitational waves. As mentioned earlier, quark stars could produce unique gravitational wave signatures, particularly during stellar mergers or collisions. By using highly sensitive detectors like LIGO and Virgo, scientists could potentially detect these waves and trace them back to their origin, providing valuable information about the properties of quark stars. Another method that might help in the search for quark stars involves studying the behavior of matter around extremely dense objects. When a quark star interacts with nearby matter, such as a companion star or a gas cloud, the intense gravitational forces could cause the matter to emit high-energy radiation, such as X-rays or gamma rays. By monitoring these emissions, astronomers might be able to identify potential candidates for quark stars. However, this approach would likely require the development of more advanced space-based observatories capable of detecting faint or unusual radiation patterns. The next generation of telescopes, such as the James Webb Space Telescope, JWST, and the European Space Agency's Athena mission, will play a crucial role in enhancing our ability to study the extreme environments around quark stars. These telescopes are designed to observe the universe in wavelengths beyond the capabilities of current instruments, including infrared, X-ray, and even gamma-ray wavelengths. With these advanced tools at our disposal, we may be able to detect signatures of quark stars or their interactions with surrounding matter, offering new insights into their nature and behavior. Additionally, the growing field of multi-messenger astronomy could also aid in the study of quark stars. Multi-messenger astronomy involves the simultaneous observation of different types of cosmic signals, such as electromagnetic radiation, gravitational waves, and neutrinos, from the same event or object. By combining data from various observatories and instruments, scientists can obtain a more complete picture of the phenomena occurring around quark stars. This approach has already proven successful in the detection of neutron star mergers, where gravitational waves and electromagnetic radiation were observed together for the first time. Applying this methodology to the study of quark stars could provide even more detailed information about their properties and behaviors. As we continue to probe the mysteries of quark stars, the role of theoretical models cannot be overstated. While observational data will be crucial in confirming the existence of these objects, it is the theoretical work that lays the groundwork for understanding what we might be looking for. Physicists and astronomers have developed various models to describe how quark stars might form and behave. These models are grounded in our understanding of quantum chromodynamics, QCD, the branch of physics that deals with the strong force and the interactions between quarks and gluons. In particular, the equation of state, EOS, for quark matter is a key component of these models. The EOS describes how quark matter behaves under different conditions of pressure, temperature, and density. It is an essential tool for understanding the internal structure of quark stars and how they might differ from other compact objects like neutron stars. However, due to the extreme conditions inside quark stars, the EOS for quark matter is still not fully understood, and there are many competing theories about how quarks might behave at such high densities. Some models propose that quark stars could be made of a dense, uniform state of quarks, while others suggest that the quarks could form exotic particles or even a superfluid state. These models have significant implications for our understanding of the forces at play inside quark stars and could help guide future observations. The development of more accurate theoretical models will be crucial in identifying potential quark star candidates and distinguishing them from other types of celestial objects. One of the major challenges in studying quark stars is the lack of direct evidence for their existence. Despite the many theoretical arguments in favor of their existence, no definitive observations have yet been made. This is not unusual in the world of astrophysics, where many ideas begin as theoretical concepts and only later become confirmed through observation. The detection of gravitational waves from a quark-star merger or the discovery of unusual X-ray emissions from a quark star would mark a major breakthrough in our understanding of the universe. In the meantime, astronomers and physicists continue to refine their models and conduct simulations to predict what quark stars might look like and how they might behave. These simulations involve modeling the dynamics of quark matter under extreme conditions and simulating how quark stars might interact with other objects in their environment. By comparing these simulations with existing data from neutron star mergers and other compact objects, scientists can begin to develop a clearer picture of what quark stars might be like and how they fit into the broader context of stellar evolution. Moreover, the search for quark stars is not only about discovering a new class of celestial objects. It also serves as a valuable testing ground for some of the most fundamental theories in physics. The study of quark stars provides a unique opportunity to explore the behavior of matter under extreme conditions, test the limits of general relativity and quantum mechanics, and deepen our understanding of the strong force that binds quarks together. These questions are at the heart of some of the most profound mysteries in modern science, and the discovery of quark stars would represent a significant step toward answering them. Quark stars could also hold the key to unlocking the mystery of dark matter. Although the precise nature of dark matter remains one of the most challenging puzzles in astrophysics, some scientists have speculated that quark stars or similar objects might be related to dark matter. If quark stars exist, they could potentially account for some of the missing mass in the universe, contributing to the overall amount of dark matter. This connection could help solve one of the most perplexing questions in cosmology, and provide a deeper understanding of the large-scale structure of the universe. Quark stars are an exciting and intriguing possibility that could significantly expand our understanding of the universe. While their existence has not yet been definitively confirmed, the theoretical and observational work being done to study these objects is pushing the boundaries of astrophysics and particle physics. If quark stars do exist, they could offer new insights into the fundamental forces of nature, the behavior of matter under extreme conditions, and the mysteries of the cosmos. As our observational capabilities improve and our theoretical models become more refined, we may one day uncover the secrets of quark stars, shedding light on one of the most fascinating and mysterious aspects of the universe. As we look to the future, the continued exploration of quark stars offers numerous exciting possibilities. But to understand just how profound these possibilities are, we must step back and consider the role these objects might play in our broader understanding of the universe. The study of quark stars touches on fundamental questions about the very nature of matter and the forces that govern the cosmos. By pushing the limits of our understanding of dense matter, quark stars could eventually unlock secrets about the early universe, stellar evolution, and even the true nature of space-time itself. The quest to understand quark stars isn't simply about discovering exotic objects that exist in the distant reaches of space. It's a search for answers to some of the most profound questions in physics. For example, how can matter behave at the extreme densities that quark stars may exhibit? This question bridges the gap between the known and the unknown in physics, offering insights into quantum mechanics and general relativity, two pillars of modern physics that have yet to be fully reconciled. Quark stars might be the perfect testing ground for a new theory that successfully unifies these two branches of physics. Furthermore, the exploration of quark stars could shed light on how the universe's most extreme objects, such as black holes, form. As we continue to refine our understanding of how matter behaves under extreme conditions, we may find that quark stars represent a critical transitional stage between more familiar objects like neutron stars and the even more enigmatic black holes. Their discovery would provide valuable insight into the processes that occur in the final stages of stellar evolution and the limits of gravitational collapse. One of the most fascinating aspects of quark stars is their connection to the idea of a quark-gluon plasma. This is the state of matter that is believed to have existed just after the Big Bang, when the universe was so hot and dense that quarks and gluons could exist freely, not confined within protons and neutrons as they are today. Studying quark stars could allow scientists to recreate and study this primordial state of matter, offering a glimpse into the conditions that existed at the birth of the universe. As technology advances and our observational capabilities improve, the search for quark stars will likely intensify. New telescopes and observatories are being developed with the express purpose of detecting the faintest and most elusive cosmic phenomena. Instruments like the Event Horizon Telescope, which captured the first image of a black hole, and the upcoming Nancy Grace Roman Space Telescope will enable us to probe the universe with unprecedented precision. These tools, coupled with the continued development of gravitational wave observatories like LIGO and Virgo, could open new frontiers in our understanding of quark stars. Theoretical models, too, will continue to evolve, becoming more detailed and sophisticated as we learn more about the behavior of quark matter. Computer simulations will play a crucial role in helping us understand the internal structure of quark stars and predict how they might behave under different circumstances. With each new discovery or simulation, our understanding of quark stars will become clearer, leading to new avenues of research and, hopefully, groundbreaking discoveries. The ongoing search for quark stars could also reveal previously unknown types of matter and energy, possibly even new forms of dark matter. Dark matter, which makes up approximately 27% of the universe, remains one of the biggest unsolved mysteries in physics. Some researchers believe that quark stars could be connected to dark matter, either by providing insight into its nature or by being composed of exotic particles that are part of the dark matter puzzle. If quark stars are found to be a significant contributor to dark matter, they could reshape our understanding of the universe's composition and help solve one of the most important questions in cosmology. It's worth noting that while quark stars are an exciting possibility, they are not the only exotic objects that challenge our understanding of the universe. The cosmos is full of mysterious phenomena that push the boundaries of what we know about physics. From the still mysterious properties of dark energy to the quest for a theory of quantum gravity, the universe continues to present challenges that require new ideas and innovative approaches. The discovery of quark stars would be a major milestone in this ongoing journey, but it is only one piece of the puzzle. In some ways, the pursuit of quark stars is a reflection of humanity's insatiable curiosity and desire to understand the universe. Every new discovery in astrophysics, whether it be a new class of stellar remnant, a strange cosmic event, or a groundbreaking theoretical model, adds to our ever-growing understanding of the cosmos. Quark stars are a natural extension of this process, as they represent a step into the unknown, a glimpse into a realm where our current knowledge is stretched to its limits. The search for quark stars also highlights the importance of collaboration and the collective effort of scientists around the world. Discoveries in astrophysics often require the combined expertise of astronomers, physicists, mathematicians, and engineers, all working together to solve complex problems and answer profound questions. The study of quark stars is no exception. Whether it's developing new models, building better observational tools, or analyzing data from space-based observatories, the quest to understand these mysterious objects is a global effort that brings together some of the brightest minds in science. As we look ahead to the next decade, it seems clear that the study of quark stars will continue to captivate researchers and the public alike. Whether or not we are able to confirm their existence in the near future, the pursuit of knowledge about these exotic objects will undoubtedly lead to new insights and discoveries that deepen our understanding of the universe. From understanding the fundamental forces that shape matter to exploring the limits of the known universe, quark stars represent an exciting frontier in our quest for cosmic understanding. The discovery of quark stars could mark the beginning of a new era in astrophysics. These objects, if they exist, could provide us with a wealth of information about the behavior of matter under extreme conditions and give us a deeper understanding of the processes that shape the universe. As we continue to explore the mysteries of the cosmos, quark stars may emerge as one of the most significant and fascinating discoveries of our time, offering us a glimpse into a universe far more complex and mysterious than we ever imagined. As we continue to probe the depths of space, the role that quark stars could play in our understanding of the universe becomes increasingly intriguing. While the possibility of their existence is still largely theoretical, the implications of their discovery would be profound. If these strange objects turn out to exist, they would bridge the gap between the most extreme forms of matter we already know and the even more exotic realms of physics that still elude us. Their study could provide insights into the nature of spacetime, the behavior of fundamental particles, and even the ultimate fate of the universe. In many ways, quark stars represent the next frontier in the exploration of dense stellar remnants. These objects are theorized to form when a neutron star, having exhausted the energy needed to support its extreme gravity, reaches a critical point where its protons and neutrons are no longer able to maintain their structure. Instead, these particles would break down into their constituent quarks, forming a quark-gluon plasma. This would create an entirely new phase of matter, one that could provide important clues about the early universe, when quarks and gluons roamed freely before the formation of protons and neutrons. But what would the universe look like if quark stars were a common feature of the cosmos? Imagine a universe where these exotic objects populate the space between more familiar stellar remnants. In such a scenario, quark stars might be responsible for a variety of cosmic phenomena that we still don't fully understand. For instance, they could help explain some of the mysterious gamma-ray bursts that have been observed, as their unique properties might lead to highly energetic events. Similarly, their gravitational interactions could be a source of gravitational waves, ripples in spacetime that are often the result of catastrophic events such as black hole mergers. The role of quark stars in the broader cosmic environment would also depend on their distribution. If they do indeed exist, they would likely be found in the densest and most extreme regions of the universe, where neutron stars and black holes are already common. This might include the cores of supernova remnants, or areas where massive stellar explosions have occurred. The dynamics of these regions, where gravity is so intense, would undoubtedly be influenced by the presence of quark stars, perhaps even altering the behavior of nearby black holes or influencing the formation of other cosmic structures. To fully understand the implications of quark stars, scientists will need to study them from multiple angles. One of the most exciting prospects is the potential for direct observation. While observing quark stars directly may be difficult due to their extreme distance and the faintness of their light, astronomers could still detect their presence through their interactions with other objects in space. The gravitational pull of a quark star, for example, might affect the orbits of nearby stars or planets, creating observable shifts in their paths. These gravitational interactions could be detected by future space telescopes or through the use of gravitational wave observatories, which are already capable of detecting the faintest ripples in space-time. Another potential method of studying quark stars would involve examining the radiation emitted by their extreme environments. Quark stars, much like neutron stars and black holes, could produce high-energy radiation in the form of X-rays or gamma rays. This radiation could provide a valuable clue to their internal structure and composition. However, detecting this radiation would be no easy task. Given the distances involved and the faintness of the signals, astronomers would need highly sensitive instruments to pick up these elusive signals. Theoretical models will also play a crucial role in our understanding of quark stars. Current models suggest that quark stars may have properties that are radically different from other types of stellar remnants. For example, quark stars could be much smaller in size compared to neutron stars, yet still incredibly dense. This could mean that they are more compact than we previously thought, with gravitational forces that are even more extreme than those of neutron stars. Their interiors may consist of a dense soup of quarks and gluons, with exotic forms of matter that challenge our current understanding of physics. As we continue to refine our models and observations, it's possible that we will find other ways in which quark stars differ from the objects we already know. They could, for example, be more stable than neutron stars, or they might exhibit unusual behaviors under certain conditions, such as rapid rotation or magnetic fields that are far stronger than anything we've seen before. These differences could have significant implications for our understanding of how matter behaves under extreme conditions, and could lead to breakthroughs in our knowledge of quantum mechanics, general relativity, and the fundamental forces of the universe. Perhaps one of the most intriguing questions surrounding quark stars is their potential role in the formation of black holes. As we discussed earlier, quark stars are theorized to be an intermediary step between neutron stars and black holes. If this is the case, then studying their formation and collapse could provide valuable insights into how black holes form in the first place. It's possible that quark stars could provide a bridge between the known physics of stellar remnants and the unknown physics of black holes, offering a glimpse into the mechanisms that drive the formation of these enigmatic objects. The discovery of quark stars could also have far-reaching implications for our understanding of the universe's early history. As we mentioned earlier, quark-gluon plasma was the state of matter that existed just moments after the Big Bang. If quark stars do indeed exist, they could provide us with a window into this primordial state of the universe, offering clues about how matter and energy behaved in the earliest moments of cosmic history. By studying quark stars, scientists may be able to reconstruct the conditions of the early universe and gain a better understanding of how the cosmos evolved from its hot, dense beginnings to the vast, structured universe we see today. Ultimately, the discovery of quark stars would mark a major milestone in our understanding of the universe and its fundamental workings. These mysterious objects could help answer some of the most pressing questions in physics, such as the nature of matter, the behavior of fundamental particles, and the forces that govern the cosmos. Moreover, they would likely lead to the development of new technologies and techniques for observing the universe, pushing the boundaries of what we can detect and study in the cosmos. In the coming decades, as our observational capabilities continue to improve, it's likely that we will learn more about quark stars and their role in the universe. Whether or not we find direct evidence of their existence, the search for quark. As we continue our exploration of quark stars, we delve deeper into the implications they may have for the future of astrophysics. Their potential discovery and study could open new doors in our quest to understand the most extreme forms of matter in the universe. With each step closer we get to understanding these enigmatic objects, we must acknowledge that the complexity of the universe only grows with every new mystery unraveled. One of the most fascinating aspects of quark stars is how their presence could reshape our understanding of other stellar phenomena, especially the life cycles of massive stars. In a typical scenario, when a star exhausts its nuclear fuel, it undergoes a process that leads it to either collapse into a white dwarf or a neutron star. For stars that are even more massive, the outcome might be the formation of a black hole, an object so dense that not even light can escape its gravitational pull. However, quark stars add an interesting layer to this process, suggesting that there might be an intermediate phase between neutron stars and black holes. If quark stars exist, they would occupy a unique niche in the stellar life cycle, challenging our current models of how stars evolve under extreme gravitational pressure. Instead of collapsing into a black hole immediately, some stars could potentially undergo a transformation into a quark star before reaching that final stage. This could lead to a new phase in stellar evolution, one where these exotic objects shine for a time before eventually succumbing to the immense gravitational forces around them. Such a phenomenon would require astronomers to rethink the very processes that govern star death and the formation of black holes, potentially leading to a major overhaul of our models of stellar evolution. The energy dynamics of quark stars are another area of active research. Like neutron stars, quark stars would likely possess extremely strong magnetic fields and intense rotational speeds. These factors could give rise to extraordinary energy emissions, potentially making them powerful sources of radiation. If quark stars were common in certain regions of the universe, they could contribute to the background radiation that we observe from distant galaxies. Understanding the energy output of quark stars could also help us better understand the role of extreme energy sources in shaping the evolution of galaxies and large-scale cosmic structures. In terms of cosmic evolution, the study of quark stars could also offer clues about the fate of the universe itself. Their formation and ultimate collapse might hold the key to understanding the ultimate end of matter in the cosmos. As scientists strive to comprehend the mysteries of dark energy, the expansion of the universe, and the possibility of a Big Rip scenario, quark stars might provide an important piece of the puzzle. Could they be involved in the process of entropy, helping to facilitate the inevitable winding down of the universe's energy? If quark stars eventually decay into even more exotic forms of matter or radiation, their study could offer a glimpse into the long-term future of the universe, helping to answer some of the most profound questions in cosmology. While much remains theoretical, the implications of quark stars reach far beyond the world of astrophysics. These objects could provide insights into the fundamental nature of matter itself. The quarks that are theorized to compose quark stars are the building blocks of protons and neutrons, yet they have never been observed in isolation under normal conditions. Quark stars might provide the first opportunity to study quarks in their natural, unbound state, shedding light on the strong force that holds particles together. By studying the behavior of quarks in such extreme conditions, we could uncover new laws of physics that govern the fundamental building blocks of matter. As we look toward the future, one of the most exciting aspects of quark star research lies in the potential for technological advancements that could enhance our ability to detect and study these objects. Current telescopes and detectors, while powerful, are still limited in their ability to observe objects in such extreme conditions. However, with the rapid advancement of technology, it's likely that future space observatories will be equipped with the necessary instruments to study quark stars directly. These advancements could include more sensitive gravitational wave detectors, which would allow us to detect the subtle ripples in spacetime created by the collapse of quark stars. Additionally, the development of more advanced space telescopes could enable us to observe the high-energy emissions from quark stars and gain a deeper understanding of their behavior. The search for quark stars is also tied to broader efforts in the field of theoretical physics. Researchers are constantly refining their models of matter under extreme conditions, and quark stars could serve as a crucial testing ground for these theories. For example, one area of focus is the study of quantum chromodynamics, QCD, the theory that describes the behavior of quarks and gluons. QCD is notoriously difficult to test under ordinary conditions, but the extreme environments of quark stars might provide an ideal laboratory for testing its predictions. By examining how quarks interact in these environments, scientists could gain new insights into the behavior of matter at the most fundamental level. In addition to theoretical physics, the discovery of quark stars could also have profound implications for our understanding of black holes. As we discussed earlier, quark stars are thought to exist in a space between neutron stars and black holes, raising the possibility that they could play a crucial role in the formation of black holes. Understanding the conditions that lead to the collapse of a quark star into a black hole could offer valuable insights into the mechanisms that govern black hole formation. This could help resolve some of the long-standing mysteries about black holes, such as what happens at the singularity, and how information is preserved in a black hole. By studying quark stars, we may be able to shed light on the nature of the most enigmatic objects in the universe. One of the most intriguing aspects of quark stars is their potential role in understanding the early universe. As we mentioned earlier, quark-gluon plasma existed in the early moments of the Big Bang, and the study of quark stars could provide a window into this primordial state of matter. By studying quark stars, scientists could gain valuable insights into the conditions that existed just moments after the birth of the universe. This could help us understand how the first protons and neutrons formed and how the universe transitioned from a hot, dense state to the vast, expanding cosmos we see today. Quark stars might serve as a bridge between the primordial universe and the present, offering clues about the fundamental processes that shaped the evolution of the cosmos. The potential discovery of quark stars would mark a monumental step in our understanding of the universe. These exotic objects could unlock new insights into the behavior of matter, the forces that govern the cosmos, and the mysteries of black holes, quantum physics, and the early universe. While much remains to be discovered, the study of quark stars promises to be one of the most exciting areas of research in the coming decades, pushing the boundaries of what we know about the universe and our place within it. Whether or not quark stars exist, their search represents the cutting edge of science, where the unknown becomes a tantalizing frontier that drives our insatiable curiosity about the cosmos. As we continue to probe deeper into the mysteries of quark stars, it's important to acknowledge the broader implications of their potential existence. Beyond simply expanding our knowledge of stellar evolution and fundamental physics, quark stars could help us answer some of the most pressing questions in cosmology. These questions pertain to the nature of space-time itself, the forces that drive the evolution of the universe, and the very fabric of reality. For instance, quark stars, due to their extreme nature, may offer vital clues in our understanding of the concept of gravity. Einstein's theory of general relativity has served as the cornerstone of modern physics, describing the interaction of mass and space-time. However, when it comes to black holes, there are still gaps in our understanding of how gravity behaves at singularities, points of infinite density. Quark stars, with their peculiar properties, could provide a bridge between our understanding of regular matter and the incomprehensible singularity of a black hole. By studying the forces at play within quark stars, researchers might be able to develop models that reconcile the macroscopic view of gravity with quantum mechanics. In addition, quark stars could potentially help us examine the limits of general relativity itself. General relativity predicts that when a massive object collapses, it will eventually lead to a singularity, a point where the laws of physics as we know them break down. The transition of a neutron star into a quark star, if indeed such a process occurs, would provide a test of this theory. If quark stars exist, we may need to reconsider aspects of relativity, potentially revising our understanding of how matter behaves under extreme conditions. This could ultimately lead to a more complete theory of gravity, one that incorporates the quantum effects we observe at subatomic scales. Equally fascinating is how quark stars might change our understanding of the cosmos on the largest scales. The formation and eventual fate of quark stars could offer valuable insights into the evolution of galaxies and even the future of the universe. As quark stars evolve, they may eventually collapse into black holes, and their radiation and gravitational effects could influence the galaxies in which they reside. Studying their dynamics might allow scientists to better understand how matter behaves under extreme gravitational forces and how it contributes to the formation of galaxies and other large cosmic structures. Quark stars could also offer answers to questions about the density and behavior of dark matter. Dark matter, the mysterious substance that makes up a large portion of the universe's mass, has been a long-standing puzzle for astrophysicists. While its presence is inferred by gravitational effects on visible matter, it remains undetectable by current methods. However, quark stars may offer an indirect way of studying dark matter. The hypothesis that quark stars could form in regions with high concentrations of dark matter could provide new insights into how this elusive substance interacts with regular matter. As scientists continue to investigate the nature of dark matter, quark stars may provide a crucial piece of the puzzle, helping to unlock one of the greatest mysteries in modern science. At the same time, the potential discovery of quark stars would raise numerous new questions, leading to further exploration and investigation. For example, how would quark stars behave in different environments? Would their properties change depending on the presence of surrounding matter, such as dark matter or other exotic particles? What would the electromagnetic and gravitational waves produced by quark stars tell us about the nature of spacetime? Could they provide insights into the dynamics of other extreme cosmic phenomena, such as gamma-ray bursts, supernovae, and the formation of black holes? Understanding the behavior of quark stars could also lead to technological advancements in other areas of science and engineering. For instance, their potential role as sources of powerful radiation might drive the development of new technologies for harnessing or mitigating high-energy emissions. The study of quark stars could also inspire innovations in our understanding of high-energy physics, materials science, and computational methods for simulating complex systems under extreme conditions. The search for quark stars could ultimately lead to a greater understanding of the most fundamental aspects of the universe. By pushing the boundaries of current knowledge, researchers may uncover new dimensions of spacetime, novel interactions between fundamental forces, and deeper connections between matter and energy. This search is not just about finding a new type of star, it's about reshaping our understanding of the universe and our place within it. The quest for quark stars will undoubtedly be a long one, but the potential rewards are immense. As technology continues to advance, and as we refine our understanding of the physics that govern the cosmos, it's possible that we may one day observe a quark star directly. Whether through the detection of gravitational waves, the observation of high-energy emissions, or the discovery of exotic matter, the confirmation of quark stars would be one of the most significant achievements in modern astrophysics. Perhaps one of the most profound implications of quark stars is how they challenge our perceptions of the universe itself. The very existence of such objects would show us that there is still so much we don't understand about the cosmos. The more we learn about these exotic stars, the more we realize that the universe is far stranger and more complex than we could have ever imagined. Just when we think we have a grasp on the cosmos, something like quark stars emerges, pushing the boundaries of human knowledge further than ever before. In many ways, the search for quark stars is not just a scientific endeavor, it's a philosophical one as well. It asks us to reconsider our place in the universe, our understanding of the laws that govern it, and the very nature of reality. Are quark stars a mere theoretical curiosity, or do they represent a new frontier in our quest to understand the universe? What can their discovery teach us about the limits of science and the mysteries that still lie beyond the reach of our knowledge? As we look to the future, we must remain open to the possibility that quark stars, like many other cosmic phenomena, may defy our expectations and challenge our most fundamental assumptions. Whether we find them or not, the journey to uncover these strange, elusive objects is part of the larger quest to understand the universe in all its vastness and complexity. The pursuit of quark stars, and the scientific inquiry that drives it, is a reminder of the power of human curiosity, the depth of our intellectual ambition, and the unrelenting desire to push the boundaries of knowledge. The study of quark stars is one of the most exciting and potentially transformative areas of astrophysics. If these objects truly exist, they could revolutionize our understanding of stellar evolution, gravity, and the very nature of matter. As we continue to explore the cosmos and unlock its many secrets, quark stars stand as a tantalizing mystery, one that may one day help us answer some of the most profound questions in science. Their potential discovery would not only deepen our understanding of the universe but also inspire future generations of scientists to continue the search for knowledge, no matter how mysterious or elusive the answers may be. Quark stars, though still theoretical, have the potential to completely alter our understanding of how stars evolve under extreme conditions. Their study could lead to breakthroughs in many scientific fields, from fundamental physics to cosmology. As we continue to explore the universe, the idea of quark stars becomes more than just an intriguing possibility. It could be one of the key pieces in the puzzle that unlocks the mysteries of the cosmos. As we delve deeper into the nature of these elusive stars, we must first understand what makes them so unique. A quark star is a hypothetical type of compact star that is made primarily of quark matter, an exotic form of matter that consists of quarks and gluons, the fundamental particles that make up protons and neutrons. In some ways, quark stars could be seen as a bridge between neutron stars and black holes, both of which are already enigmatic objects in their own right. Understanding quark stars may provide insight into the forces that govern the evolution of such extreme objects. Neutron stars, which are the remnants of massive stars that have undergone supernova explosions, are incredibly dense objects. A neutron star is formed when a star with a mass between 1.4 and 3 times that of the Sun collapses under its own gravity, causing its protons and electrons to combine and form neutrons. These neutrons are packed tightly together in a sphere about the size of a city, yet with a mass greater than the Sun. This creates a star that is both incredibly small and dense. However, neutron stars themselves may not be the ultimate state for all stars of this mass range. If the mass of a neutron star exceeds a certain limit, known as the Tolman, Oppenheimer, Volkoff limit, it will no longer be able to support itself against gravity, leading to a collapse that could form a quark star. A quark star is hypothesized to form when the neutrons inside a neutron star are crushed into their constituent quarks. This process would result in a star made of quark matter, a state of matter that is far more exotic than the ordinary matter we experience every day. Quark matter is theorized to be a dense soup of quarks and gluons, the fundamental building blocks of matter. Under normal conditions, quarks are confined within protons and neutrons. But in the extreme environment of a collapsing star, these quarks could be freed from their protons and neutrons and form a new phase of matter. This quark matter would be so dense and energetic that it would be unlike anything seen in nature before. The properties of quark stars are still speculative, but scientists have proposed that they could be even denser than neutron stars, with densities approaching the limits of our understanding of matter. If quark stars exist, they could represent the densest known objects in the universe, places where the very fabric of matter itself is being torn apart and reformed under the influence of extreme gravity. Despite the theoretical nature of quark stars, there are compelling reasons to believe that they could exist. Observations of neutron stars, particularly through gravitational wave detections, have already revealed much about the nature of these extreme objects. In fact, the study of neutron stars could be key to understanding quark stars, as both share many similarities in terms of their formation and evolution. One of the most intriguing aspects of quark stars is how they might bridge the gap between neutron stars and black holes. While neutron stars are incredibly dense, they still have a defined surface and are capable of emitting light in the form of X-rays and gamma rays. Black holes, on the other hand, have no surface and possess an event horizon, beyond which nothing can escape, not even light. If quark stars exist, they could be a stepping stone between these two objects. It's possible that, as a quark star collapses further, it could eventually form a black hole. In this way, quark stars could help us better understand the processes that lead to the formation of black holes, one of the most mysterious and intriguing objects in astrophysics. The study of quark stars also raises important questions about the behavior of matter at extremely high densities. As we approach the limits of matter's density, we begin to encounter the effects of quantum mechanics and general relativity in ways that are not yet fully understood. Quark stars could provide a natural laboratory for studying these effects, allowing scientists to explore how gravity, quantum mechanics, and the fundamental forces of nature interact at scales far beyond what we can currently replicate on Earth. In addition, quark stars could offer new insights into the structure of the universe itself. The discovery of quark stars would have far-reaching implications for our understanding of the formation and evolution of stars, galaxies, and even the fabric of space-time itself. As we study these exotic objects, we may uncover new clues about the origins of the universe, the nature of dark matter and dark energy, and the future evolution of the cosmos. While the existence of quark stars has not yet been confirmed, their potential to reshape our understanding of the universe cannot be overstated. The search for these mysterious stars will continue to push the boundaries of astrophysics and cosmology, leading to new discoveries and deeper insights into the nature of the cosmos. Whether we find them or not, the quest to uncover the secrets of quark stars will undoubtedly be one of the most exciting and transformative endeavors in the history of science. Ultimately, the study of quark stars is not just about understanding a new class of objects in the universe. It's about understanding the fundamental forces that govern the cosmos and the laws that govern the behavior of matter. It's about exploring the limits of knowledge and pushing the boundaries of what we know to be possible. In doing so, we may uncover new truths about the universe and our place within it, truths that could change our understanding of reality itself. As technology advances and our methods of observation become more refined, the discovery of quark stars could be within our reach. When that day comes, it will mark a new chapter in our exploration of the universe, opening up new frontiers in astrophysics and offering answers to some of the most profound questions about the nature of existence. The study of quark stars, like so many other mysteries of the cosmos, is a reminder that the universe is far stranger and more complex than we could have ever imagined. And so, we are left with the tantalizing possibility that somewhere in the vastness of space, beyond the reach of our current instruments, there could exist these enigmatic objects, quark stars, waiting to be discovered. Whether they are out there, lurking in the depths of space, or whether they remain a theoretical curiosity, the search for quark stars will continue to captivate the imagination of scientists and explorers alike, pushing us ever forward in our quest to understand the mysteries of the cosmos. As we continue our exploration of quark stars, it's important to consider not only their theoretical existence, but also how their discovery would reshape the field of astrophysics. The implications of finding a quark star would be monumental, not just for understanding these exotic objects themselves but for providing a deeper understanding of the universe as a whole. For instance, their discovery could offer valuable clues about the end states of stellar evolution, particularly in stars that collapse into compact objects like neutron stars, and potentially, quark stars. We know that stellar remnants, objects that are left behind after stars exhaust their nuclear fuel, can take different forms, depending on the mass of the original star. If a star's core remains stable after the supernova explosion, it may become a white dwarf. If the core is more massive, it can collapse into a neutron star. If the core's mass exceeds the threshold of about 3 solar masses, the neutron star can collapse into a black hole, a singularity with infinite density. This progression is fairly well understood, yet quark stars offer a fascinating possible alternative stage that might occur before a black hole is formed. The concept of quark stars has implications that extend beyond astrophysics into fundamental physics. These objects might allow us to test some of the most profound theories of modern physics, such as the nature of quantum chromodynamics, QCD. QCD is the theory that describes the strong force, one of the 4 fundamental forces of nature, which governs the interactions between quarks and gluons. This theory remains one of the most challenging areas of study in particle physics, and the possibility of quark stars presents an opportunity to test this theory in extreme environments, beyond anything we can replicate in terrestrial laboratories. Quark stars could also shed light on the mysterious, and still largely unexplained phenomenon of dark matter. Dark matter, which makes up about 27% of the universe's mass-energy content, does not emit, absorb, or reflect light, making it invisible to current instruments. Its existence is inferred from gravitational effects on visible matter, and its properties remain a subject of intense speculation. Some scientists have hypothesized that dark matter could consist of exotic particles, such as axions or weakly interacting massive particles, WIMPs. Others have suggested that quark stars could contribute to the dark matter content of the universe. The unusual properties of quark stars, with their dense quark matter, may offer a clue or a piece of the puzzle in understanding this mysterious form of matter. If quark stars indeed exist, they might also have a significant impact on our understanding of gravitational waves. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as the collision of black holes or neutron stars. These waves were first detected by the Laser Interferometer Gravitational Wave Observatory, LIGO, in 2015, and their study has since become a major area of research in astrophysics. The properties of quark stars, particularly their density and behavior in extreme gravitational fields, could lead to unique gravitational wave signals. If quark stars were to merge or undergo other violent processes, they could generate gravitational waves with distinct patterns that scientists could use to confirm their existence. Moreover, quark stars could provide valuable insight into the physics of compact objects and the behavior of matter at extremely high densities. The transition from ordinary matter to quark matter would occur at densities far beyond what we can study on Earth. Understanding how matter behaves under such extreme conditions could unlock new discoveries in materials science, quantum mechanics, and even our understanding of spacetime itself. One of the major challenges in confirming the existence of quark stars is the fact that these objects would be extremely difficult to observe directly. Their size would likely be similar to that of neutron stars, making them hard to distinguish with current observational techniques. Furthermore, the radiation emitted by quark stars would differ significantly from that of normal stars or neutron stars, adding another layer of complexity to their detection. Theoretical models predict that quark stars could emit bursts of energy in the form of gamma rays, X-rays, or neutrinos, but the precise characteristics of their emissions remain uncertain. As our detection methods evolve, it may become possible to detect these signatures, but for now, much of the evidence for quark stars remains circumstantial. Despite these challenges, there are several avenues through which scientists might detect quark stars. One approach is through the study of the equation of state of ultra-dense matter. The equation of state describes how matter behaves under extreme conditions, such as those found in the cores of compact objects like neutron stars. If the matter inside a neutron star becomes dense enough to form quark matter, the equation of state would change dramatically. By studying the properties of neutron stars, such as their mass and radius, scientists can infer whether they are composed entirely of neutrons or whether they might contain quark matter. This indirect method could provide the first clues about the existence of quark stars. Another method for detecting quark stars involves the study of gravitational waves. As mentioned earlier, quark stars could generate unique gravitational wave signals when they collide or undergo other violent processes. By analyzing the frequency, amplitude, and waveform of these signals, scientists could potentially distinguish quark star mergers from other types of compact object mergers, such as those involving neutron stars or black holes. This approach would require extremely sensitive detectors, but the detection of gravitational waves from quark stars would be a game-changer in our understanding of these mysterious objects. In addition, the search for quark stars may benefit from new advances in astrophysical observation, including the development of more powerful telescopes and observatories. For example, upcoming space-based missions like the James Webb Space Telescope, JWST, could provide unprecedented views of the universe, allowing scientists to study the behavior of matter in the most extreme environments. Similarly, the next generation of ground-based observatories, such as the Square Kilometre Array, SKA, could offer new insights into the properties of compact objects and their role in the universe. The concept of quark stars also raises fascinating questions about the ultimate fate of matter in the universe. If quark stars do exist, they may represent a stable endpoint for certain types of stellar evolution, providing a kind of middle ground between neutron stars and black holes. Alternatively, quark stars could be a transient phase in the life cycle of stars, with their ultimate fate depending on their mass, composition, and the surrounding environment. Could quark stars be the precursors to the formation of black holes? Or could they exist in stable equilibrium for millions or even billions of years, offering a new type of celestial object for us to study and explore? Ultimately, the search for quark stars is not just about finding new types of stars, it's about exploring the nature of the universe at its most fundamental level. These mysterious objects could provide insight into the forces that govern the behavior of matter, the nature of space and time, and the evolution of the cosmos. The discovery of quark stars would be a landmark achievement in the field of astrophysics, offering new answers to some of the most profound questions about the universe. Whether they exist or not, the study of quark stars will continue to inspire and challenge scientists, driving us ever closer to a deeper understanding of the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe.